good evening. No matter where you are, welcome to our new Connections in Number Theory and Physics workshop day 2. I have a couple of announcements to make before we actually start. First of all, the reminder that we're recording all the talks. So in particular, if you ask a question and you don't want to be on the recording, you should actually ask the question via the chat, and I will try to read it out then. Secondly, there is a transcript, live transcript going on. You can find it in your Zoom menu at the bottom of your screen. Either you can turn it on or off, so that's really up to you. And it's supposed to help you with understanding what's being said, at least language-wise. And third, the success of the breakout rooms yesterday was a big and happy surprise to all of us. And so we decided to have breakout rooms today as well. So like yesterday, there's going to be an official discussion session beginning maybe at 5:30 or so after the discussions of the last talk have ended. So the breakout rooms are accessible through Zoom. Some of you have had problems to access breakout rooms, so we do encourage you to update your Zoom to the latest version, because the older versions of Zoom seem to have created some problems. And other than that, there will be further help on entering the breakout rooms when we reach that time of the day. But for now, let's hear the first talk, and it's my very big pleasure to announce Boris Pioline from Paris, who will tell us about exact BPS couplings and black hole counting.
Thanks a lot, Catherine. Can you hear me?
Yeah.
Okay, well, thanks a lot to the organizers for putting up this nice program and for the kind invitation to speak. It would clearly have been much more fun to all meet in Cambridge and have lively discussions, but I guess I will have to wait for another year. So the title of my talk is Exact BPS Couplings and Black Hole Counting. And it will be based on a series of papers with my collaborators listed below. Just want to single out my longtime collaborator, Sergei Alexandrov, who was rebaptized yesterday as Sergei Abramovich in his talk. And Sergei does know his Abramovich Tegun handbook of integrals in and out, but okay, he's Alexandrov. Anyhow, so there'll be also some overlap with Steve's talk yesterday. In the first part of my talk, which will be about the maximally or supersymmetry case. But I also intend to cover the case of n equal to 4 supersymmetry and n equal to 2 supersymmetry times permitting. Now I can see a problem here. Okay. For a second, my screen was frozen. Is it okay? Can you see the poster of the 2016 Simon's workshop?
Yes, it's there.
All right. So for those who attended this workshop, in fact, my talk will be kind of an updated version of a talk which I gave at that time. And in fact, most of the open questions which I had raised have been answered since then, thanks to the work of my collaborators. And so that will be what I intend to talk about. Very good. So the main motivation, at least from my side, is to understand the precision counting of BPS black hole microstates in supersymmetric string vacua. And clearly, since the seminal work of Strominger-Vafa in '95, a lot of work and a lot of progress has been made in this direction. And it has uncovered exciting connections with many areas of mathematics, algebraic geometry, representation theory, and automorphic forms, which is the most relevant for this audience. So for string vacua with n equal to 4 supersymmetry or higher in 3+1 dimensions, there is by now a complete understanding, I would say, of the exact of the BPS indices which count black holes in such string vacua. So the BPS index omega as a function of the charge Q is given by Fourier coefficient of some modular form, either a classical weakly holomorphic modular form of SL2Z, or more fancy objects such as Jacobi forms or Siegel modular forms, especially in the n equal to 4 case. And this precise formula allows very detailed tests of the Bekenstein-Hawking formula, which predicts the growth of these BPS indices as the charge is scaled up, and also gives access to subleading corrections to these formulas. So it gives precise tests of validity of string theory as a quantum theory of gravity. Now, an important phenomenon in these studies, especially for supersymmetry n equal to 4 or lower, is that the BPS index is actually not just a function of the charge Q, but also a function of the moduli Z, which determine the internal 6-dimensional space in 4 dimensions. And it's discontinuous across certain real codimension 1 walls in moduli space. Therefore, it jumps from one integer to another one. And that's very well understood physically as the appearance or disappearance of multi-centered black hole bound states, which exist in one region and not in the other one. So that phenomenon is relatively mild for n equal to 4 supersymmetry, in the sense that only bound states with 2 centers contribute. And so the dependence on the moduli is simply encoded into a choice of integration contour for the Fourier in extracting the Fourier coefficient. And you also know precisely the contributions from the 2-centered bound states. Therefore, you can subtract them. And you discover, in particular, that the indices which count single-centered black holes are actually Fourier coefficients of mock Jacobi forms, which are another interesting piece of related to number theory and automorphic forms. So this was the remarkable result of Taboka Muti-Zaghi. Now, in n equal to 2 string vacua, the situation is more challenging. The precision counting is much less advanced. So in the context of type 2a strings compactified on the Calabi-Yau 3,4x, the BPS indices of interest are well-defined mathematical quantities. They are known as the generalized Donaldson-Thomas invariants of the category of coherent sheaves on X. So they are well-defined, but they are notoriously difficult to compute. And one can hope to use automorphy to constrain them, but that's complicated by various facts. One is that the moduli space of generic Calabi-Yau 3-folds is no longer a locally symmetric space, in contrast to the n equals 4 and n equals to 8 case. And as a result, the U-duality group is typically much smaller. 4 dimensions is just the monodromy group of the Calabi-Yau 3-fold. And the other complication is the one I already mentioned, it's contributions of multi-centered black holes bound states. But now they can involve an arbitrary number of constituents, and so it's much more delicate or difficult to subtract them. So for some years, I've advocated an approach to this problem of counting BPS states in given dimension, let's say d+1 dimensional string vacua, which is to consider certain terms in the low energy effective action after you reduce from d+1 dimensions down to d on a circle of fixed radius r. So the idea here is that any BPS state in dimension d+1 is a solution with a finite energy, which is independent of time. It descends to an instanton configuration of action r times the mass after reduction on the circle. And therefore, if you consider particular terms in the low energy effective action, they will pick out instanton corrections exactly from the black holes that live in 1 dimension higher. So a famous example of this philosophy is a 3-dimensional QED, which was analyzed by Polyakov in 1977. And Polyakov pointed out that the Topf-Polyakov monopole in 4 dimensions, which is a static solution, descends to an instanton configurations in 3 dimensions, which generates some potential in the action, which accounts for confinement. Now, of course, we're interested in supersymmetric settings, and in that case, because these states break some of the supersymmetries, they will carry certain fermionic zero modes. So if you have a state that breaks k over the k supercharges of the vacuum, it will descend to an instanton which carries k fermionic zero modes. Therefore, its contribution will vanish unless the zero modes are saturated. In other words, they will only contribute to interactions in the low energy effective action, whose number which carries sufficiently many fermions to be saturated. More precisely, the number of fermions plus twice the number of space-time derivatives should be bigger than the number of fermionic zero modes. Recall that the space-time derivative of a boson is related by supersymmetry to a pair of fermions. So I have a little table here of what are these Well, so the BPS couplings are interactions which where this number f plus 2n is strictly less than the total number of supercharges of the vacuum. And as a result, they only get contributions from instantons which preserve some fraction of supersymmetry. So in this little table, I gave various examples of BPS couplings for various supersymmetry. So in the maximally supersymmetric case, which is n equals 8 supercharges in 4 dimensions of 32 real supercharges, the most symmetric instanton configurations preserve half of the supersymmetry, so they carry 16 zero modes. As a result, they can contribute to 16 fermion term in the low energy effective action, or 8 derivative terms, and that's the famous R to the 4 coupling, which Steve talked about at the beginning of his talk yesterday. Now, if you consider black holes or BPS states which preserve only 1/4 of the 32 supersymmetries of the vacuum, they will carry 24 fermionic zero modes. Hence, they can contribute to terms with 12 derivatives. Grad 4 R4 is an example of such terms. And well, in 4 dimensions, the last possibility is when the states preserve 1/8 BPS, 1/8 of the supersymmetries, have 28 fermionic zero modes, therefore can contribute to 14 derivative terms. That's a grad 6 R4. So the first part of my talk will be to review this progress on such couplings in maximally supersymmetric vacua. Then I'll turn to half maximally supersymmetry, n equal to 4 in 4 dimensions. Here, the half BPS-saturated couplings are of the form f to the 4, where f is some Maxwell field strength, or r squared. R is the Riemann tensor, of course. Whereas if you want to probe quarter BPS states, then you want to look at the d square f to the 4 or f square r square and so on. Finally, in the most challenging case of n equals to 2 supersymmetry, the half BPS states have 4 fermionic zero modes, so they will contribute to the 2 derivative effective action, and in particular, they will renormalize the metric on moduli space. So what are the general expectations that we have for such couplings? Well, first of all, these couplings after reduction on the circle of dimension r will depend on the radius r, on the moduli in dimension d+1, as well as on the holonomies of the n gauge fields around the circle. So at large radius, the moduli space in dimension d roughly factorizes as a product of r plus times md+1 times this torus Tn. Of course, the torus is fibered over md+1, so that's a very sketchy way of writing it out, but it carries the idea. Now, we're interested in counting 4-dimensional BPS states, so we want to compactify down to 3 dimensions. In that case, because of the duality between gauge fields and scalars, the torus Tn will actually be doubled to a symplectic torus of dimension 2, T2n. And in the presence of gravity, we have one additional scalar, which is the dual of the Kaluza-Klein gauge field, the off-diagonal part of the metric. And so this scalar is sometimes called the knot potential, and it lives on the circle bundle over T2n. So this is kind of a twisted torus. So those are the variables that these couplings depend on. What we expect is that in the limit r goes to infinity, the coupling in d dimension will go like some part of r times the coupling in dimension d+1, plus an infinite series of exponentially suppressed terms that go like e to the minus the radius times the mass of the BPS state with charge q, sum over q, along with some imaginary, well, some phase coupling to the holonomies. And the coefficient of such terms is expected to be the BPS index, more precisely the helicity supertrace, which counts BPS states with the right number of fermionic zero modes. So it can be defined as the trace of the angular momentum to J3 to the n weighted by a proper by fermionic parity. Now, this formula is very sketchy. As you see, there are dots here, and there are many dots, in fact. So one is that there'll be in general additional power-like terms which due to massless threshold effects, which correspond to couplings in higher dimension, but at lower order in the derivative expansion. Another source of corrections are loop corrections around each instanton sector, which will change this exponential behavior into some marginal asymptotic series in inverse powers of R. So typically turn it into some Bessel function, which is constrained by supersymmetry. There will also be multi-instanton contributions coming from scattering states of black holes in higher dimensions. And those are actually needed to smoothen out the jumps of the helicity supertrace as you across the walls of marginal stability. And finally, for gravitational theories in three dimensions, there will be also contributions that depend on this nut scalar coming from so-called top nut instantons, which decay faster, like e to the minus r squared, but are in fact very much relevant since this sum over charges here has zero radius of convergence. If we believe in the Bekenstein-Hawking, then we expect this omega n to go like exponential of the entropy, which is of order q squared. So this has zero radius of convergence, but you can estimate the ambiguity of this series and convince yourself that it's on the right order to be fixed by these top-nut instances. So the take-home message is that these BPS couplings in dimension d after reduction on the circle provide a natural generating series of BPS indices in dimension d+1, which is similar in spirit to the naive black hole partition function, where you would just be summing over Q of these BPS indices weighted by e to the minus their energy. But it's actually better behaved, and in fact, it's well defined, unlike this formal definition, which does not converge. So it's not only better defined, but also much more constrained. So for vacua with 4 supersymmetry or higher, the moduli space in any dimension is a locally symmetric space. And in particular, it admits a group of an arithmetic subgroup acting on that space. So the so-called duality group, and we expect that any function, any term in a low energy effective action will be invariant under that group. So this function is expected to be an automorphic function under this duality group in dimension D. I say function, not form, because it may not satisfy the precise definition of an automorphic form as an eigenmode of all differential operators. But it has to be invariant, and that's a strong constraint. It guarantees that the Fourier coefficients will be invariant under the duality group in 1 dimension higher. But in fact, it's much more than that, because you want the full sum to be invariant under this group in dimension D. So that's a very powerful constraint. It's not so powerful for n equal to 2 string vacua, because as I said, the duality group, the model is broken, is much smaller than for higher supersymmetry. In fact, if you think of type 2a on the Calabi-Yau x times this circle of radius r as M theory on x times T2, then you expect these couplings to be invariant under the SL2Z acting on the torus T2 times the monotony group of the Calabi-Yau times some discrete Heisenberg group acting on the twisted torus of holonomies. And well, that's not a simple reductive group, but it's still rather powerful, and you can hope to get strong constraints on the DT invariance by enforcing this property. So in the remainder of this talk, I will survey 3 instances of this philosophy. First one are the D6 R4 couplings in maximally supersymmetric theories. Second part will be n equal to 4, so I will look at 6 derivative couplings. And finally, if time permitting, I will talk about these instanton corrections to moduli space for n equal to 2 string vacua, based on the work with the authors listed down here. The upshot is that in the first 2 cases, we recover the known counting of 1/8 BPS states in the first case, or 1/4 BPS states in the second one. well, in more detail than was known before, probably. But in addition, we encounter new types of automorphic forms which may be of interest to mathematicians, or maybe not. It's for the mathematicians to tell. In the third case, on the other hand, we find strong constraints on the DT invariants. In particular, we find that for those DT invariants supported on devices, meaning that they count D4, D2, D0 bound states, the generating series have to be mock modular forms of higher depth. So I hope I'll be able to say a few words on that at the end. So I think that's a good time to break for questions if there are any.
Boris, I have a question. These counting functions typically are written in terms of duality invariance. Is that taken care of by a formula, or?
Yes, so by construction, once you extract Fourier coefficients of an automorphic form under this three-dimensional duality group, it will be invariant under the action of the group which commutes with a large reduced limit. So it will be automatically invariant under the duality group in 4 dimensions, which doesn't mean that it will be just a function of the quartic invariant, let's say, of E7. It might involve some discrete invariance, but invariance on the duality in 4 dimensions is guaranteed by construction.
I see. And the formula on the previous slide is also invariant under that?
That formula?
Yeah, the one on top, yeah.
Yeah, so that formula is not the formula. It's only a caricature.
Okay.
But yeah, as I said, so the Fourier coefficients that you will extract from this coupling will be invariant by construction. So you'll see some examples where that comes out clearly.
Thank you.
All right, so let's start then with the n equals to 8 setup, which was partly discussed by Steve yesterday. So as you know very well, when we compactify string theory on the torus TD, we expect the duality invariance under ED+1, which is generated by the T-duality group SODD and by the global diffeomorphisms of the torus SLD+1. And so these couplings are at order R4 and grad 4 R4 are completely understood. They are strongly constrained by word identities and by perturbative corrections. They are given in any dimension by an Eisenstein series or Lagrange Eisenstein series of the U-duality group, where at least in dimensions where you don't hit the pole of this Lagrange Eisenstein series. Otherwise, they might have to be more careful, but I'm just giving the general picture here. So this Lagrange Eisenstein series can be written, defined à la Lagrange as a sum. So given a parabolic subgroup pk of G corresponding to some highest weight lambda k, you sum over all images of character yk to a certain power, or in all images, so all elements in G modulo those which leave the character invariant. Or equivalently, you can think of them as constrained lattice sums, where you sum over all all vectors in a certain lattice, which transforms in the corresponding representation to this highest weight lambda k. There is some quadratic form, invariant quadratic form on that lattice, and also some quadratic constraints, which ensures that all the vectors are in the image of a single vector, so to speak. So those are quite simple and basic automorphic forms, very well known to mathematicians. And it's well known how to extract their weak coupling expansion. One reproduces the known tree-level 1-loop or 2-loop contributions, plus infinite series of Dean-Stockton corrections. And if you apply this philosophy to this Eisenstein series, you can read off what are the Fourier coefficients. And indeed, you confirm that they are weighted by the helicity supertraces omega 8 or omega 12, which counts the number of BPS states preserving either 1/2 or 1/8 of the supersymmetry. Those indices are rather boring, namely they are only 0 or 1. Well, the non-boring part is that they are actually 0 unless the charge corresponds to a half BPS orbit. So that's why those automorphic forms are associated to small representations, but otherwise this number is 1, at least for primitive vector here. I'm restricting to primitive vectors. And for the quarter BPS case, where it's the Fourier coefficients are given by some divisor sum, they depend on manifestly invariant combinations of the charge vector Q. So this Q cross Q here is the Jordan quadratic product on the lattice of electromagnetic charges. So this is a quadratic constraint, which is the half BPS constraint. And here you have a cubic constraint. This I4 is the quadratic invariant of the charge Q, and I4 prime is its gradient. So this is a cubic constraint. And so the wavefront set of these automorphic forms are exactly in agreement with the physical prediction of having corrections only from half BPS or quarter BPS states. So that's all nice, but these numbers are boring, and they don't grow exponentially because they don't correspond to large black holes. So let's turn to grad cis R to the 4, which should get contributions from 1/8 BPS states. Well, it cannot be an Eisenstein series because the Wardan entities, the supersymmetry constraints, require that it should not be an eigenmode of the Laplacian. Rather, it should be it should satisfy some inhomogeneous equation whose right-hand side is the square of the R to the 4 coupling. That's a very old, well-known story by now. And so the question is to determine the exact such function subject to it's the weak coupling expansion and large radius expansion. So what we expect is that this function automorphic form will have Fourier coefficients weighted by the known helicity supertrace for 1/8 BPS black holes, which was computed back in 1999 in 5 dimensions, and later extended to 4 dimensions in the reference below. So we expect for such black holes that the helicity supertrace grows exponentially, and in fact it should be given by coefficients of the weak holomorphic form given as follows here. So indeed you can check that using the usual Rademacher expansion, if you like, that their growth is exactly in agreement with the Bekenstein-Hawking. So can we find such an automorphic form? Yeah, well, we can. In fact, there are various proposals, or there were on the market a few years ago. One is a proposal which I put forward in, well, one was the original one by Pierre Van Hooggreen and Michael Green in 10 dimensions, which will be a special case of the one I give later. But a somewhat different one in spirit was given in 6 dimensions as a theta lift. So in mathematical terms, it's a theta lifting of genus 2 real analytic Siegel modular form known as the Kawazumi-Zheng invariant. So integrated against a narrowing theta series at genus 2 for a lattice of dimension 5, 5. In such a way that the product will be an automorphic form, an automorphic function of for the group spin of SO55. And you also have, turns out you have to add some Eisenstein series for this is the spin 55 actually, which is an homogeneous solution needed to match the perturbative terms. So this Kawazumi-Zheng invariant here is in fact familiar from the genus 2 computation of this coupling in string theory, carried out by these authors. So at 2 loop, you find that the correction to D6R4 is a similar theta lifting, genus 2 theta lift of the Kawazumi-Zheng invariant times the lattice partition function. In 6 dimensions, this would be gamma 4, 4, and the non-perturbative completion is obtained by extending 4, 4 to 5, 5 dimension signature 5, 5 lattice. So I refer to Eric's talk in a few minutes for a definition of the Kawazumi-Zheng invariant. It's not really important for what I have to say. But so that was one proposal. Another one was valid in generic dimension. And the idea here was to covariantize the 2-loop supergravity amplitude. Here, basically the idea was to covariantize the genus 2 string theory amplitude. But you could do the same for the 2-loop supergravity amplitude. That's what Guillaume Bossard and Kleinschmidt did in 2015. well, genus 2 two-loop amplitude in supergravity roughly looks like this. So you have this sunset diagram with the edge of length L1, L2, L3, which you need to integrate over. And you need to sum over all states which run into these two loops. So states of charge Q1 in the first loop and Q2 in the second loop. So I'm cutting a long story short to justify or to motivate these ansatz for the exact D6 alpha coupling in dimension D. So you see it appears as an integral over the fundamental domain of SL2Z with a parameter tau here, which is actually not the genus 1 of the string, but rather the shape of the sunset diagram. If you change variables from Li to tau and V using this prescription due to these authors, you can integrate over the overall scale of these Schwinger parameters, and you're left with an integral over the shape of so a constrained theta series or Epstein-like series where you sum over charges Q1 and Q2 running in the two loops. And then there is this additional factor here, which you can obtain from a supergravity computation, which is basically once you divide out by V, a sum, well, this combination of Schwinger parameters. But if you extract out the power of volume, it just becomes a function of this modulus tau here. It's so it's a locally polynomial function in tau 1 in the standard fundamental domain of F. But it can be extended to the Hupperath plane by modular invariance. It produces what's known as a local modular form. And so this object is well defined, well subject to some convergence issues, and that was proposed as an exact version, exact candidate for this coupling. Well, in these recent papers with Guillaume Bossard and Axel Kleinschmidt, we actually expanded out on this proposal and checked the various limiting behavior. And there were a few interesting mathematical lessons to come out of this, so we'll just focus on these lessons. One is that the agreement between the two proposals hinged on the property of this Kawazumi-Zheng invariant. You have to relate an integral over genus 1 to an integral over genus 2, so to moduli spaces, and that comes out once you realize that this Kawazumi-Zheng invariant is actually a Poincaré series of this object A of tau, which is nothing else but the tropical limit of Kawazumi-Zheng invariant. So that's a formal identity. It needs regularization, but that's what it boils down to, without any further details. And so those two proposals are actually consistent with each other. And moreover, we can compute the large reduced expansion for either of them using the Fourier expansion of this Kawazumi-Zheng invariant, which in turn is accessible because it admits a theta lift representation. So you see there are many theta liftings in this story. They should not be confused with each other. So if you remember this weakly holomorphic form that was counting quarter BPS, 1/8 BPS states, well, this had the weight minus, so 2 minus 3 is minus 1. So if you use the raising operator d rho and integrate it against the Siegel theta series for a lattice of signature 3,2, that produces a function on the Grassmannian of signature 3,2, which is the same as the Siegel Hupperath plane, because SO32 is the same as SP4 roughly. And indeed, this is a non-trivial, this is non-trivial identity, which was conjectured from string theory and then proven using rigorous methods. So I'm not giving any details, but as a result of this connection, you can extract the coefficients of these exponentially suppressed terms in the Fourier expansion and recover the fact that they are weighted exactly by the Fourier coefficients of this weakly holomorphic modular form, as expected from the microscopic counting. So that's an example of automorphic form, or automorphic object, if you like, in that case on the group E8, which has exponentially large Fourier coefficients. Of course, it's not in the usual Langlands type of landscape. Now I'm going rather superficially here, so there are many details, and in particular, beyond these corrections from 1/8 BPS states, there are also instanton, anti-instanton corrections, as well as Calusa-Klein monopoles. It's a long story, which I have to cut short. So I'd like now to move on to the case of n equal to 4 string vacua, which will give rise to some similar type of automorphic functions, namely genus 2 theta liftings, but now of different type of Siegel modular form. So just to remind you, so n equal to string vacua occur as, for example, type 2 on K3 cross T2 or heterotic on T6. Now, well, as before, the moduli space is a symmetric space, but it factorizes in 4 dimensions as the product of Poincare upper half plane times orthogonal Grassmannian. If you reduce further on a circle, it becomes a simple moduli space, a simple orthogonal Grassmannian of signature 024, 8. You can convince yourself that if you expand that at large radius, you reproduce the structure I was giving before, the radius times the 4-dimensional moduli space times this twisted torus. Here I'm just giving it locally. Or if you look at the perturbative expansion, weak coupling expansion, it includes the dilaton as well as the Narain moduli on T7. So here I have in mind heterotic on T6 description, which is now heterotics on T7, etc. So again, we'd like to find an automorphic form on this orthogonal Grassmannian, which counts 1/4 BPS states in 4 dimensions and corresponds to a particular BPS-saturated coupling in the low energy effective action. So it should be an automorphic form of signature 24/8. Yeah, so the kind of couplings we want to look at are 6 derivative couplings. So the 4 derivative coupling will have contributions from half BPS, and the 6 derivative guy will have contributions from 1/4 BPS. And so we need to, of course, use supersymmetry constraints to determine this, to have any chance of determining these couplings uniquely. So this analysis was done in a series of papers with Guillaume Bossard and my student at the time, Charles Cosnioro. So you see they have the supersymmetry constraints are rather similar to the one of the R4 coupling and D6 R4, namely there are homogeneous differential equations of second order for the first case and inhomogeneous equations of second order with a source term given by the square of the lower coupling. So by themselves, these identities actually imply that the F will be perturbatively exact at 1 loop in heterotic perturbation theory, whereas G will be exact at 2 loop in heterotic perturbation theory. So because of lack of time, I will just focus on the second in this story, the 1/4 BPS saturated guy. So we expect that the coefficients of that automorphic form should match the degeneracies of 1/4 BPS diodes. Well, that's a well-known story going back to diagram in the 96. Namely, they can be extracted as Fourier coefficient of a meromorphic Siegel modular form, the inverse of the Iguzakas form of weight 10. Now, because this is meromorphic, there is an ambiguity in the choice of contour. But it was understood by Chen Berlinder that there is a natural contour C to pick up, to extract the Fourier coefficient, such that whenever it depends on the moduli in 4 dimensions, and whenever the moduli cross a wall of marginal stability, this contour will cross a pole of 1/phi10, and the discontinuity turns out to match the contributions from half BPS states. It's easy to extract them from the factorization properties on the separating locus in the moduli space Siegel upper half plane. So that's a should be a familiar story to a number of you. And as a result, the jump in this helicity supertrace is the product of the BPS indices counting 1/2 BPS states with charge Q1, P1, Q2, P2, weighted by the symplectic product or the Dirac product of electromagnetic charges, just corresponding to the expected degeneracy of a two-centered bound states. So that part was, of course, already well known. And now the question is, can we come up with a natural proposal or a unique identification for this coupling as an automorphic form on the Grassmannian of signature 24,8. Well, the input in some information that we have are, of course, the tree level, one loop and two loop contributions to it. As usual, they are given by integrals over genus 1 moduli space or genus 2 moduli space. So for the one loop part, it's an integral of the ordinary Narijn theta series of proper signature with some insertion of polynomial to carry the indices. So this is a polynomial in the lattice vectors which are summed over in this Siegel Narijn theta series, times some almost modular, almost automorphic modular form. And more interesting at genus 2, well, Docker and Fong in 2005 computed such as, well, basically four graviton scattering of, actually 4 gauge boson scattering in 10 dimensions, from which you can easily reduce down to 3 dimensions and dualize your gauge bosons into scalar fields. So from their analysis, you can also extract the genus 2 correction to such coupling. It's again a theta lift now of, well, 1 over phi 10, rather interestingly, again, some theta series with the quartic polynomial insertion. So this 1 over phi 10 here a priori has a different origin as the one from before. The one from before was just guessed. This one is made through a bona fide two-loop computation in string theory. Well, given this, it's not too hard to come up with a proposal for the exact coefficient of this coupling. Check, of course, that it satisfies the differential constraints as it should. In fact, the inhomogeneous term here, it just comes from some boundary contribution due to the pole of this Iguzakis form in the separating degeneration. And once you have the idea to look at this object, you can try to extract its expansion both in weak coupling and at large radius, and see whether it matches expectations. That's some game that we did over several years with Guillaume and Charles. And once again, we confirm the expectation that the contributions. So there are a variety of Fourier coefficients to this object, but if you focus on those corresponding to quarter BPS black holes, so with the largest suborbit, so to speak, and then you can demonstrate that they are weighted by the Fourier coefficients of 1 over phi 10, exactly in the chamber specified by this or guessed by Cheng and Freleng. So you would say that's a lot of hard work for something that we knew already. Well, that's partly true. One of the good things is that it works for any such model with n equal to 4 supersymmetry, including CHL models. So you can actually generalize this DVV ansatz for any such model and obtain precise predictions also for non-primitive charge vectors and so on. So again, it's something which I don't have really time to go over, but feel free to open these long papers that we wrote to check out any of the details. Now there are also things which are less well understood, namely contributions from instanton anti-instantons, as well as Kaluza-Klein monopole contributions. Very well, so I see that I have like 5 minutes left in my official time. Maybe that's a good time to pose for questions on these two stories here, n equal 8 or n equal to 4.
Boris, I have another question. In this formula on this page, is some automorphic property of the left-hand side supposed to be manifest?
Yes, it's supposed to, and if it's not, that means I gave a bad talk. So on the left-hand side, you integrate a Siegel modular form against a theta series of signature in 24,8. That means that the result will be invariant under the automorphism group of the lattice of signature 24,8.
Right.
So that the left-hand side is therefore an automorphic form on the Grassmannian. Automorphic function. It's not an automorphic form, well, because it doesn't satisfy this differential identity. Also, it has poles on various divisors, but then it's manifestly invariant under three-dimensional duality group, and therefore, again, by construction, once you extract Fourier coefficients in a large radius limit, they will be manifestly invariant under under the SL2Z cross SO 622. And in fact, the end result is a formula exactly of that type. So is that answering your question?
Yeah, half my question. So the other half was, what about the SP2Z of the?
Oh yeah, that's an excellent point. Thank you. So indeed, from this point of view of DVV, it was quite mysterious why the generating series of quarter BPS states should be invariant, should be given by some Siegel modular form with SP4Z invariance, whereas the only non-trivial part of the invariance here was the SL2Z, which is a subgroup of SP4Z. Now, from this construction, on the other hand, the origin of this is clear because it comes from a genus 2 string computation, where at least the crucial part input is the genus 2 string computation, which has manifestly the SP4Z invariance. So in a way, this is explaining or giving some underlying reason for the occurrence of SP4Z in n equal to 4 dione counting.
I see. And the meromorphicity doesn't play any, doesn't introduce any subtlety in the statement.
Well, no, it does actually introduce many subtleties. Part of it is well, so the integral here is well defined, despite the poles. The function is integrable. There is okay. I suppress this discussion, but there is of course some regularization you have to do in the infrared, so, which I'm suppressing. But once you subtract these terms, the integral is well defined. Now, when you extract the Fourier coefficients, of course you have to take into account the fact that they depend on the contour, but the contour is predicted by the physics. You don't have to invent it.
Thanks.
Okay, thanks a lot for your questions. Okay, so in the remaining 5 minutes, I guess I will try to go over the n equal to 2 story. Again, that would be rather superficial and more like a teaser, because it's hard to go into details in such a short time. But the same philosophy applies once again. So the half BPS coupling that we want to look at is a metric correction to the metric on vector moduli space in 3 dimensions. So we take type 2 string on Calabi-Yau x times a circle, and we expect to see corrections from BPS black holes in 4 dimensions, along with the Kaluza-Klein monopoles. Now, this metric is of course a complicated object. So it must be quaternion killer by supersymmetry, and we know its form in the large radius limit, because we know what's the moduli space in 4 dimensions using mirror symmetry. But there is some technology to describe the quaternion Keller metrics using analytic data. The technology is called twistor space. So rather than looking at the metric, we're going to look at some symplectic structure on the twistor space, which is a P1 bundle over that quaternion Keller space. And well, this is actually a long program which I've been involved for quite a long time by now. At this point, we know exactly how to describe this d-instanton corrected twistor space through a system of TBA-like equations, which are quite similar to the one introduced by Gaoto, Moore, Knightsky in the study of gauge theories in 3 dimensions. We don't know how to include at this point Kaluza-Klein monopoles. We had some early work with Daniel Pearson to understand that. I'll say a word later. But so we can already consider this information about the instantons is already enough to extract strong constraints on the DT invariants, which enter in this system of TBA-like equations. And the non-trivial constraints come from the fact that this moduli space must admit an isometric action of S2Z, once again coming from the T2, which is manifest in the M-theory description. So I'm just going to summarize what those constraints are. If the instantons corresponds to D4, D2, D6, D4, D2, D0 branes on the Calabi-Yau. If you just look at D0 branes, so corresponding to sheaves supported at a point, well, S duality requires that the DT invariant should be equal to minus the Euler number of the Calabi-Yau. That's because this coefficient also determines the one loop correction to the metric, and S duality mixes one loop correction with these D0 brane instantons. That's something which was realized very early on. Now, if you increase the support of the sheaf, consider a sheaf supported on a curve plus n times the point. Well, the same logic shows that the BPS index weighting such instantons, so counting such sheaves, has to be related to the Gromov-Witten invariants entering in the tree-level metric through this multi-cover sum. That's essentially because S duality mixes worldsheet instantons with the D2 branes wrapped on the curve. Again, I apologize for not giving more details. I'm just calling the results here. If you increase the dimension of the support of the sheaf and now allow for a sheaf supported on the divisor, that means a D4 brane with some D2 and D0 brane charge. Then from this study, you conclude that the generating series of these indices in the particular chamber known as the attractor chamber. So you make a generating series where you let the D0 brane charge become arbitrary, but you fix the D4 and D2 brane charge. Well, you discover just by analyzing the correction to the metric that this series should be a weakly holomorphic modular form of prescribed weight and multiplier system. That actually was known before, thanks to the work of Malles and Strominger-Witten, using a different reasoning, but it comes out from this idea of just looking at the particular BPS coupling and analyzing the constraints from S duality. The reasoning of MSW was in terms of the wrapped fibrine on the D4, on this 4 cycle, giving rise to some superconformal field theory. Now we can add something to this whole story, however, which is that if you consider D4 branes not on an ample divisor, but on a reducible divisor, which is the sum of effective divisors DI, then it requires actually a lot of analysis, which I can't do here, but you conclude that it should no longer be a weakly holomorphic modular form, but rather a mock modular form, whose depth is the number, is n-1, where n is the degree of reducibility of this divisor. Now, what does mock modular form mean? Well, just to complete here, if finally gamma was supported on the full Calabi-Yau 3, that means corresponding to the D6 brane wrapped on Calabi-Yau 3, then S duality relates this index to the effect from the topological string partition function, to the effect of Kaluza-Klein monopoles, which come from topological string partition function. And I should say that at this level, there is very little understanding of the constraints of S duality. So that's something left for the future. But to go back to this mock modularity of D4 brane instantons or D4 brane Donaldson-Thomas invariants. So we're using essentially this twistor construction of the metric, we could establish that the generating series HP corresponding to DT invariants with fixed magnetic charge P, that is fixed D4 brane charge P, are not modular invariant by themselves, but they can be completed in a very explicit way in terms of generating series associated to the various components of the decomposition of the divisor. So the various pieces in which this divisor can split with some prescribed prefactor, which has an expression in terms of sum over trees, of product of certain error functions or generalized error functions associated to the tree. Unfortunately, I cannot go into details at this point, although I could if I'm asked questions. In such a way that this object is non-holomorphic in contrast to HP itself, but the full sum has to be modular in order for the metric to be invariant under SI2Z, and that's a very strong prediction for DT invariance. The notion, the name of depth n-1 is reflects the fact that the holomorphic anomaly. So this object has a holomorphic anomaly. It's not holomorphic, but its anomaly is determined in terms of the generating series for the lower for the constituents of the divisor. Now that looks like a little bit like abstract formulas, but they can be made very, very concrete. And in fact, they have been made concrete in the special case of local Calabi-Yau4, which is the canonical bundle over some surface. In such a case, the DT invariants counting D4 branes wrapped on the surface are the same as the vacua invariants. And the formulas which are given here, in fact, predict the modular completion of the generating series of vacua invariants of arbitrary rank. Now, in view of time, I think I have to stop here. That's essentially what I wanted to say, and just to finish up with a summary. So, I think by now we have demonstrated that this approach of looking at BPS-saturated couplings after reduction on the circle is quite powerful, and we can use the power of automorphy to constrain and sometimes compute the BPS indices. There are still some dark spots, namely the contributions from DD bar instantons and Kaluza-Klein monopoles remain to be fully understood. And well, finally, to collect perhaps with reality. So the story I told you about was about the in n equal to 2 case was about the vector multiplet moduli space in type 2 and Calabi, of course, S1. But it's actually identical to the issue of hypermultiplet moduli space in type 2b on X after using mirror symmetry or just T duality on the circle. And so it might also have some implications for string phenomenology as well. So thanks a lot for your attention, and apologies for going over question time.
Thank you very much, Boris. Cannot see it, but there's a lot of virtual applause. We've already heard a number of questions, but I think there's time for maybe 1 or 2 quick questions. If there are any more, please raise your hand or just speak up. Well, doesn't seem to be the case. It's a little bit of a rush anyway now, so there will be more time for questions, as I announced previously, in the discussion session today, which is not officially in our program, but we've decided to have another discussion session after the 3rd talk today, similar to what we had yesterday. More about that later on. Let's thank Boris once again. And I will wait until Eric has shared his screen to start his talk. Brilliant, thank you. All right, so it's my very big pleasure to announce our 2nd speaker today, Eric Docker, who is joining us from the University of California and will tell us about modular graph functions, forms, and tensors.
Okay, well, thank you very much. And thank you very much to the organizers for putting this meeting together, even if it's virtual. So the topic of my talk today is modular graph functions, forms, and tensors. And actually, A lot of this work has been done in collaboration with Michael Green. And so a few days ago was his birthday, so happy birthday, Michael. So first of all, let me explain the words in the title a bit. A modular graph function is a map from a certain type of graph to an SL2Z invariant function on the Poincare upper half plane. Of course, I'll explain in detail what these are. They generalize non-holomorphic Eisenstein series, which we have seen discussions about in previous talks. And in turn, they may be generalized to functions that are not SL2Z invariant, but actually covariant and correspond to differential forms on the Poincare upper half plane. A further generalization is actually to higher genus. I haven't mentioned genus before, but the previous case, SL2Z, really corresponds to genus 1 Riemann surfaces. And one may generalize the notion of modular graph functions to maps of graphs into a function of the moduli space of Riemann surfaces of higher genus. Boris also mentioned Kawazumi-Zhang invariants and also faulting invariants, and they, in fact, these higher genus modular graph functions actually generalize those. In turn, they may be generalized to modular graph tensors under the higher genus modular group. Now, all of this is inspired by string theory, of course. String theory may be expanded in perturbation theory and is given as a sum over Riemann surfaces. And the low energy expansion naturally gives rise to these modular graph functions. And in particular, as already Stephen and Boris have pointed out, one is interested in the physics of the low energy expansion of string theory, and in particular in comparison with predictions from S-duality and so on and so forth. Now, actually, Steve and Boris have made my life very easy because they discussed many of the physics aspects of this. So I'm really going to concentrate on mostly the math and use the physics as a motivation. So very briefly then, perturbative string amplitudes are given by a topological expansion in the string coupling parameter. And that expansion can be organized in a sum over compact Riemann surfaces of genera going from 0 to infinity. There are declarations on this by points. These vertex points represent physically the incoming and the outgoing strings in the physical process. For a given process, the number of vertex points is fixed. So for example, physicists speak of 2 particle to 2 particle scattering, which would correspond to n is equal to 4. So how are these amplitudes calculated? Very briefly in just one line. For every genus, you integrate the n vertex points over the compact Riemann surface. The introduction part was just words, so now you see it written down, but it's just those words. And then here is the sum over Riemann surfaces, which is, I think, where I was. So Catherine, thank you very much. I hope this will now work. So for each genus, one integrates over the vertex points over the compact Riemann surface, and then finally over the moduli space of compact Riemann surfaces. For superstrings, really these integrals originate from a moduli space of super Riemann surfaces, but I will not need this here. What do you see now?
Genus 0.
All right, okay, we're making progress here. So although this will not be immediately necessary for modular considerations, let me nonetheless consider the case of genus 0 as a warm-up. So in the case of genus 0, we have the Riemann sphere, and the amplitudes involve integrals of the Zellberg type, complex Zellberg type. So integrals over C of these different powers of differences of points. The parameters S here are kinematic parameters they generalize the Mandelstam invariance for physicists. There are no S's on the diagonal, and every row and every column sums to 0. But otherwise, you can really think of these as complex parameters, and these integrals are meromorphic in these complex parameters with simple poles at non-negative integers, and those poles correspond to the exchange of massive string states. So that's the physics of those. For example, if you take the 4 graviton amplitude, and here and throughout, I'm going to omit all the kinematic factors that go with this, which already Steve and Boris referred to. So for example, for the 4-point amplitude, there is a factor of the Riemann tensor, 4 copies of it with suitable traces. And I'm just going to ignore that because I'm going to focus on the math more than on the physics here. So in the case of the 4 graviton amplitude, these integrals can actually be done, and they're ratios of gamma functions. And we're going to be interested, as also Stephen and Boris already emphasized, often in the low energy expansion. And that low energy expansion corresponds to an expansion in powers of these variables S. And so here, in the second equality, I've written an expression which is manifestly in terms of powers of S. If you expand this exponential, you will obtain a Taylor expansion in S, and the coefficients are polynomials in these zeta values, and these zeta values are evaluated at odd integers starting with 3. Okay, so in fact, already the 3-level amplitude, or so-called genus 0 amplitude, has interesting number theoretic properties. What happens for amplitudes with more than 4 gravitons? Well, there it's harder to do the integrals. You can still do an expansion in terms of Sij, and these now give rise to multiple zeta values. In fact, for the experts, to what is called single valued multiple zeta values. Okay, so this was the warm-up. So are you seeing genus 1?
Yeah.
Okay, so genus 1, the Riemann surface is now a torus, which shall represent in the complex plane by taking the plane and cosetting out by a lattice, lambda, which is generated by 1, and tau, where tau is a point in the complex plane. So throughout the complex plane, upper Poincaré half plane will be denoted by H1, and the imaginary part of tau I'll denote by tau2. So we can pick some local coordinates, complex coordinates, z and z bar, and I'm going to denote the volume form with area 1 by d mu of z. So the thing that we'll need is the scalar Green's function. So it's the inverse of the Laplacian on this surface, and we normalize it so that its integral is 1. I can write it down in a number of ways in terms of theta functions or so, but here the most useful is going to be in terms of a double Fourier series. It's convenient to decompose the points on the torus in terms of this lattice. So I'll parameterize by u and v, where u and v are in the interval 0 to 1. And so then the Green's function is given by this Fourier sum of 2 integers, not both equal to 0. This Green's function is invariant under SL2Z when tau transforms in the usual way and z transforms, well, also in the usual way if you're used to this. Okay. So the genus 1 amplitude is constructed in the following way. I'm going to define for an arbitrary number of points n, the following quantity, b, which depends on the s's and on tau, as an integral over the n points, zk, and then an exponential of the sum of these s's multiplied by the Green's function corresponding to the difference of the points I and j. Actually, the tree-level amplitude was also of this form, where the Green's function is simply the log of the difference of Zi and Zj absolute values. So this is actually a universal factor in string amplitudes, often referred to as a Koba-Nielsen factor because they introduced it. So the Sij are the same kinematic variables as for genus 0. Here there are poles at positive integers, 1, 2, 3, also corresponding to the exchange of massive string states. But because G behaves logarithmically as a function of the distance, actually the expansion around 0 for S is convergent with the radius of convergence 1. So within this radius, the function B is actually holomorphic in Sij. And so in particular, one can expand it in a Taylor expansion, which is convergent around 0. Since G is invariant under SL2Z, the measure was invariant. This is SL2Z invariant. So let me give you the example of the genus 1,4 graviton amplitude computed a very long time ago, almost 40 years ago. So it is given, well, by a kinematic factor, which I'm ignoring, and then an integral of this function B4 over the moduli space of genus 1. So the upper half plane cosetted by PSL2Z. This makes sense because B4 is invariant under SL2Z. So it makes sense to pull it back to M1. Now, this integral is a lot less convergent than the tree-level amplitude. In fact, it's only absolutely convergent when the real part of all the Sij's is 0, but an analytic continuation exists and in fact produces branch cuts in the complex planes for Sij, and these branch cuts correspond physically to the creation of virtual pairs. So this is all well understood. Now, so the amplitude is given by this integral over moduli space. In this talk, I'm actually going to mostly concentrate on the integrand and not carry out the integration. The integration is very interesting, mathematically and physically, but that's a whole other subject and a whole other set of talks. So one can organize the Taylor expansion of B, which remember is possible because B for given tau has a radius of convergence 1 in each Sij, so we can Taylor expand it, which physically corresponds to the low energy expansion. Of course, it still has to be integrated, but for the time being, I'm just going to consider the expansion of B. And this expansion can be organized in terms of what's called Feynman graphs. Physicists love Feynman graphs. And this goes back quite a ways to work by Michael and collaborators. And the organization of this expansion is as follows. Each integration point, Zi on the surface, you represent by a dot. And then the Green's function between vertices Zi and Zj is represented by an edge or a line. So this represents the Green's function. And each vertex, once you've put together all these Green's functions, is integrated against the measure that we had before for every point. And to a given order in Sij will attach a weight, will assign weight W to a graph that has W edges. Now, graphs can be reduced to simpler types of graphs. For example, if a graph is disconnected, then the corresponding value of B is simply the product of the disconnected components. And also, if you have a graph that becomes disconnected when you cut one edge, that vanishes because the integral of the Green's function alone is 0. And if you remove one vertex, then again, the graph factorizes. So in this way, you can reduce the graphs to essentially one edge irreducible graphs that are connected. So here I'm giving you some examples. So if the weight is 2, we have 2 edges, and the only thing you can write down is this graph. If the weight is 3, you can have either 3 vertices or 2 and connect in this way, and so on and so forth. Now we can organize this expansion by the weight, but actually it turns out to be more profitable and clearer to organize them by the number of loops they have. So actually to backtrack a little bit, so here is actually, one can use this as a definition of a modular graph function. We have a graph, and we will now attach to this graph an SL2Z invariant, Taylor coefficient. Okay, so I'm going to now work loop order by loop order. So let's consider one loop. So to one loop, the number of vertices is equal to the number of edges. All vertices are bivalent, and we integrate over each vertex. And the result of doing that is to have this multiple integral over W copies of the integrand, and then times the Green's functions, which are all concatenated. And the effect of doing these integrations is to set all these momenta P equal to one another. So the result is this combination where P is an element of the lattice that we encountered before. And physicists call these lattice points the momenta on the lattice. The momenta are quantized in these units. And of course, when P is equal to 0, this term would not make sense, so one removes it. So lambda prime is the lattice minus the point 0. Now this gadget you recognize up to perhaps a silly normalization that we use. These combinations are the non-holomorphic Eisenstein series. They may be, here they are defined for a weight W, which is an integer, but actually they can be defined for any complex number. And they're invariant under SL2Z here by construction, as you very well know. They're eigenfunctions of the Laplace-Beltrami operator on the upper half plane, which I wrote down here. Remember, tau2 is the imaginary part of tau. And so the eigenvalues are S times S minus 1. My Laplacian here is actually negative, which is why this is the expression. As you also know, they have an expansion near the cusp at infinity. The leading term is the constant Fourier mode. It's a power tau2 to the S and tau2 to the 1 minus S with coefficients that are essentially zeta values. One can, of course, write down the full Fourier series. There's a Poincaré series. There are eigenfunctions of Hecke operators and so on and so forth. This is extremely well known since the 19th century. So I'll consider one loop graphs completely understood. Now let's look at two loop graphs. So what happens there? Well, let's go back to our figure. So for two loops, we have two loops, but that can mean a number of different possibilities. So in particular, you see that on any leg, in some sense, you can have any number of bivalent vertices. Here there are none. Here there is one on one leg. Here there are two on this leg. And here there are two on, here there is one on each one of the legs. So that means that in general, the denominators that we have can be raised to any power, any integer power. And then the momentum, the integrations over the points dictate that the overall momentum should sum to 0. So that's what explains this delta function. So the weight is the sum of these three integers, A1, A2, A3. This sum is convergent absolutely when AR are in the positive integers, and for me it's 1, 2, 3, 4, and so on and so forth. And when convergent, then the result is invariant under SL2Z as well. So hence the name modular graph function is actually a modular function. You could, in principle, generalize these as well, as you had done for the case of the Eisenstein series, and consider them for complex A1, A2, A3. And then there are similar convergence conditions. But I'm not going to do that here because a lot of special properties arise precisely in the case when these modular graph functions arise from string theory with integer indices. So in analogy with the Eisenstein series, I'm now going to discuss several properties. So for example, the first one is the expansion at the cusp. So this was derived a few years ago by Bill Duke and myself. And what you get is that you still obtain a Laurent polynomial in tau 2 of the same degree as the Eisenstein series, namely W and 1 minus W. But now basically all intermediate terms between tau 2 to the W and tau 2 to the 1 minus W are actually populated. In the case of Eisenstein series, there were none in between. Here, they're actually all populated, and they have various number theoretic properties. So the first coefficient and the coefficients of these odd zeta values here are rational numbers, while this coefficient of this special power here is a bilinear in odd zeta values with rational coefficients. Similarly, Poincaré and Fourier series have all been also computed. I'm not going to discuss them here. What I'm going to discuss is the next topic is the Eisenstein series satisfied differential equation, a differential equation. So the question here is, do these things satisfy differential equations? Well, in fact, the answer is yes. So I'm still working on these two-loop modular graph functions. I'll call them CABC of weight W given by the sum of the indices. And so the theorem is that they are linear combinations with rational coefficients of modular functions, which I denoted here by this Gothic C. And each one of these modular functions satisfies this inhomogeneous Laplace type equation with eigenvalues which are given by S times S minus 1, just as the case of Eisenstein series. But now the S's actually jump by 2. And then there is a degeneracy N here, which goes mod 3. And there is a right-hand side, and the right-hand side is a polynomial of degree 2 of weight W in the Eisenstein series. Okay, so the differential equation is not quite as simple. There's a right-hand side. This is very similar to the equations discussed by Steve Miller in his talk. And in this case, this entire family of functions satisfies these equations. Now, some of these differential equations are actually rather special. For example, the first one, the simplest one, is the Laplacian on C111 is 6 times E3. Well, now E3 satisfies, of course, the differential equation of the Eisenstein series. And that means I can integrate this equation up to a constant. But this constant can be determined from the asymptotics at the cusp and is given by just zeta of 3. In fact, this result was computed earlier by direct summation by Siegel. I'll give you also a more complicated example, a bit more interesting. So here is at weight 9, we have this differential equation. Again, E9, I can use the equation for the Eisenstein series. I integrate up to a constant and then determine the constant by asymptotics. So in fact, from the differential equation, we can derive an infinite family of what I'll call algebraic equations. By algebraic, I just simply mean here, not differential equations. Okay, so we did 1 loop and 2 loops. What happens at higher loops? Well, I can say general things. The explicit formulas are now much more complicated, of course. It is still generally true that at the cusp, these modular graph functions have a Laurent polynomial expansion in tau 2 of the same degree, 1 and 1 minus W plus exponential terms. And the coefficients now include not just zeta values of polynomials in zeta values, but actually also multiple zeta values. And more specifically, technically, single value modular multiple zeta values. Now, in addition, they satisfy a host of algebraic identities. All of these identities, including the ones I showed you before, have uniform weight. The weight on both sides is the same, a bit like you have for the equations relating multiple zeta values. And I give you just a few here to show you what they look like. So here's a tree-loop modular graph functions related to 2 loops and 1 loops. Here's a 4 loop, and so on and so forth. Now, how do you prove these equations? Well, actually, using the Laplacian no longer works. And the reason is that the Laplace-Beltrami operator, acting on 3 loops and higher, does not map these functions into linear combinations of themselves. Now, in addition, if we go to amplitudes with more than 4 vertex points, these are actually not given just by these functions B that I showed you, but they also involve derivatives of the Green's function, in addition to just powers of the Green's function. And that produces exponents of the momenta that are unequal for the holomorphic ones compared to the anti-holomorphic ones. So we actually need to generalize. This is not general enough to have a good theory of what these things are. So here I present a general definition of what we call modular graph forms for a reason I'll explain in a second. So we consider a graph, but we consider it with decorations, which I'll call A and B. The graph has V vertices and R edges. Gamma is the connectivity matrix of the graphs. It gives you the relation between whether a vertex and an edge meet or not. And if they do, then you have the value 1 or -1, and otherwise it's 0. The decorations generalize these indices A, B, C that we had before and are given by arrays of integers, positive integers. And so to the decorated graph, we now associate, so there is the characterization of the graph by the connectivity matrix, then there are the decorations, and then there's the point in the upper half plane. And they're given similarly, but there's a momentum conservation relation at each vertex. And then the edges are now given by inverse powers of the momenta, where PR and P bar R are raised to independent powers, AR and BR. Okay. Now, if we apply an SL2Z transformation with the particular normalization I've chosen here, then these objects transform with a weight, a modular weight, written in this way. Now, the modular weight here is purely anti-holomorphic in nature. It's given in this way. So these quantities are not modular functions. They transform either as a modular, what we call modular form, or you could multiply them by suitable powers of d tau and d tau bar, and then they would be actual differential forms, which is why we dub them modular graph forms. Now here I've chosen a particular normalization. When mu is not 0, there is no canonical normalization for the powers of tau2, so this is an arbitrary choice, but a convenient one. And if the arrays A and B are identical, then mu is 0, and in fact, we recover modular graph functions. So this is a true generalization of modular graph functions. So now, these objects obey relations that are, in a sense, much simpler than the ones we had before. Momentum conservation gives you linear relations between modular graph forms with different decorations. The array SR here is an array that has zeros everywhere, except in the spot R. And so here, basically, you subtract successively all the possible locations of SR, and that gives you linear relations. Instead of using the Laplace operator, we use the mass operator, acting here on purely anti-holomorphic weight forms. And this gives you first-order differential equations. And in fact, this differential operator maps modular graph forms to modular graph forms with this very simple relation, where AR is simply the rth entry of the array A, and SR is the quantity I defined here. So in fact, using these sets of relations, one can devise an algorithm to obtain all identities between modular graph functions and forms. I'll explain it here for the simple case of modular graph functions, which is a little bit easier. So what is the algorithm? If you have a linear combination F of weight W modular graph functions, so with A is equal to B, and if they satisfy that the mass operator to some non-negative power, to some positive power on F is 0, then F is independent of tau, and then that independent part can be fixed by asymptotics. How does this in practice work? Well, you see that each time you apply this mass operator, you increase the exponents of the holomorphic part by 1 and decrease the exponents of the anti-holomorphic part by 1 as well. So as I apply more mass operators, I actually approach more and more purely holomorphic modular forms. And so the relations can then be induced from relations between holomorphic modular forms, which of course we understand very well. So this algorithm, and I of course do not have the time to explain the details, allow you to obtain all modular forms, and this has been done in practice for weight less or equal to 6. There is even a Mathematica package available to do this. Now, as you can see, there is a relation with holomorphic modular forms, so I can use these differential equations and back integrate them up using the holomorphic forms that occur. And so I've written this down very schematically here. You can have a differential equation for these quantities E, which are holomorphic or meromorphic, and which are related to an E with 1 fewer entry, and then a holomorphic standard form, the standard holomorphic Eisenstein series. And so they admit an integral representation then, and that integral representation can allow you to express the modular graph forms. These things satisfy shuffle relations and are interesting in their own way, and can be generated via a generating function. So this was done in this work here. Another generalization is that so far we have considered Feynman graphs that have no momenta inflowing or outflowing. That's easy to change, especially for a physicist. It's what we do all the time. So one can in fact generalize these modular graph functions and forms to non-holomorphic single-valued elliptic functions by introducing essentially a character. You can think of this as a character, or you can give the form characteristics. And the simplest case is prototype, if you wish, is the Siegel-Zagier single-valued elliptic polylog, which I wrote down here, which depends on 2 indices, A and B. The holomorphic and anti-holomorphic momenta again come to different powers. And here is this multiplicative character. So elliptic modular graph functions can now be defined again for an arbitrary number of loops and exponents. And I've written this down here, the loss of differential and algebraic equations, again, related to iterated integrals, but perhaps the most interesting in a number theory conferences, if you wanted to consider not modular graph functions with respect to SL2Z, but rather with respect to a congruent subgroup, then actually you could use these as a starting point. For example, for the principal congruent subgroups gamma n, I would pick the points Zi here, these multipliers, to be torsion points of degree n. Okay, that's pretty much what I wanted to say about genus 1. You see that string theory forces you to not just consider quantities on surfaces of genus 1, but also on arbitrary genus surfaces. And so the question is, well, what type of functions does this give rise to? So in short, what is our task? Well, our task is to generalize the genus 1 construction to higher genus. What did we have at genus 1? Well, I'm going to concentrate again on the integrand only, not integrate over moduli yet. And so we had an integral over all the vertex points, and we had this Koba-Nielsen factor. Very simple, actually. So if we consider a compact Riemann surface of genus H, which is greater or equal to 2, then what we need minimally is a generalization of the Green's function and a generalization of this measure of integration. So in order to get that going, let me just refresh your memory on some higher genus stuff. So the first homology group is isomorphic to Z to the power twice the genus. It's equipped, we can equip it with an intersection pairing, which is anti-symmetric. And so we can pick a canonical basis of A and B cycles and a canonical basis of dual holomorphic 1 forms, which I'll call omega I. And these indices, capital I and J, will always run from 1 to the genus here. So they can be canonically normalized on A cycles, where delta is the Kronecker delta. And then on B cycles, they give rise to a symmetric matrix, which has a positive imaginary part by the Riemann relations, which is referred to as the period matrix of the surface. In the case of genus 1, the period matrix is not a matrix, just a number, complex number, tau. And right. The Jacobian variety is given by C to the power H divided by the lattice spanned by the identity and by omega. The modular group is the group that leaves this anti-symmetric pairing invariant, and that's SP2H, Z. So it's a symplectic group of dimension 2H with, rank, I guess, H, and with integer entries. And you can decompose it in blocks of H by H matrices, A, B, C, D. And then the homology cycles are mapped as follows. It's natural to introduce the Siegel upper half plane, which upper half space, which generalizes the Poincaré upper half space and is given by H by H matrices, omega, which is symmetric and positive imaginary part. And for the special case of genus 2, the moduli space of compact Riemann surfaces is actually given by the Siegel upper half space divided by SP4Z. With a minor detail, which is you have to remove the diagonal corresponding to disconnected surfaces. Okay, so after this little introduction on higher genus, we're now going to go and try to find a Green's function and an integration measure. So actually, on any Riemann surface, sigma, there is a natural metric given by the pullback of the flat metric on the Jacobian. This metric is conformal and it's also modular invariant and gives a canonical volume form on the surface, which I've written down here. So omega is are the abelian differentials, holomorphic abelian differentials. Omega bar is just a complex conjugate. omega, capital Omega is the period matrix, and throughout I'm going to denote the imaginary part of the period matrix by y. And I can normalize this volume form to 1, to integrate to 1. The Green's function, there is a natural generalization of the genus 1 Green's function given by the inverse of the Laplacian on functions orthogonal to constants, given like so. And for the special case of the Arakelov Green's function, what one subtracts here is this canonical volume form. And we can normalize it, we normalize it to integrate to 0. So having these ingredients, there is a very natural candidate for a generating function for higher genus modular graph functions. Namely, I take this measure given by integrating over each copy of the Riemann surface, and then have a Koba-Nielsen factor where the Green's function is now the Arakelov Green's function. Okay. These integrals are again absolutely convergent in the unit disk for each of the parameters S. So there is you can do a Taylor expansion, a convergent Taylor expansion in S around 0 with radius 1. And so in fact, these Taylor coefficients in this expansion define higher genus modular graph functions. One particular set of examples of these. Now, actually, if you look at the genus to 4.4 graviton amplitude, it is not given by the previous expression. Why is that? Well, while the volume form kappa is essentially unique on a single surface, when you consider n copies of the surface, the measure kappa to the n is not unique. And in fact, as Boris mentioned in his talk, the genus 2,4 graviton amplitude is available, was computed a long time ago, and is given by this expression. So the exponential here is again the Koba-Nielsen factor, but the integration measure is more complicated. It's given by the wedge product of y times y bar, where y is this combination that involves the kinematic variables s, but also involves these bi-holomorphic forms, omega, which omega. So this object is SP4Z invariant, and so produces a suitable integrand on the moduli space of genus 2 Riemann surfaces. So let's now take this amplitude, the string amplitude for genus 2, for 4 gravitons, and expand it in powers of S. So this gives the low energy expansion. I'm going to use this symmetrical polynomial in the S's to do the expansion. And so what do we get? Well, the first term, from the point of view of the surface, is just a constant. The second term is the Kawazumi-Zhang invariant that also Boris mentioned. And then there is an infinite series of higher order terms. So the Kawazumi-Zhang invariant was encountered or was defined by Kawazumi and Zhang as a spectral invariant for the scalar Laplace operator, but it can also be recast in the following form as an integral of the Arakelov Green's function with this funny measure in the points x and y, and then contracted with the inverses of the imaginary part of the period matrix. This object is related to the genus 2 Faltings invariant and satisfies a number of interesting equations or properties. So in particular, it satisfies an inhomogeneous eigenvalue equation on the compactified genus 2 moduli space. So the equation looks like follows: delta minus 5 of phi is equal to the right-hand side. Delta here is the Laplace-Beltrami operator on the upper half, Siegel upper half space, which is invariant under SP4Z, so it descends to the Laplace operator on M2. 5 is 5, not much to be said about that. And delta Sn is the delta function which has support on the separating node, where the surface decomposes into two genus 1 surfaces. Actually, this differential equation allows you to integrate phi over moduli space. And this gives this d to the 6th, r to the 4th effective interaction that Boris and also Stephen discussed and matches with the predictions of S-duality and supersymmetry. And as Boris also explained, it admits a theta lift. So now we could go to higher orders in S and expand further. We get new invariants, which I will not write down. Now, actually, recently, we computed the genus 2 amplitude, but with 5 gravitons. That's a lot more complicated, and we used ingredients from the pure spinor and RNS formulations to do it. And then in ongoing work with Oliver Schlotterer, we're actually also deriving at least part of it, the NS sector, from the RNS formulation alone. Now here there are many kinematic invariants as opposed to the single one we had for 4 gravitons. In particular, there are 17 new integrals generated on 5 copies of the Riemann surface. I'm just giving you some examples. Here there is the ever Koba-Nielsen factor, and then these deltas are these biholomorphic forms that we saw before, and Y is the imaginary part of the period matrix. So needless to say, this largely enlarges our dictionary of these higher genus, or in this case, genus 2 modular graph functions. And the natural question is, well, are there any non-trivial identities between them? So how does one go about thinking about this? Well, at genus 1, we had to generalize to modular graph forms. That was the natural setting for a simple formulation. Here, since the modular group is now SP and is higher rank, the natural object is actually a higher genus modular graph tensor. And this actually goes back to work of Kawazumi, unpublished work, I must say, in the first part of the last decade. So how does the construction go? Well, I'm going to give you the special case where there are no derivatives of the Arakelov-Green's function. So one can introduce this matrix of one forms on sigma, given like so, where we leave the indices now free. Before, in this pullback of the canonical metric on the Jacobian, we had contracted them, but here I'm now going to leave them free. That's the right thing that actually enters here. This object, this matrix, transforms as a tensor under the modular group, like so. And now I can consider, just as an example, 2 objects. The first one is an open chain of modular graph tensors. There are no loops in this. I start with a point, I have a link to another point, I have a link to another point, and end up at a final point. The Kawazumi-Zhang invariant is a special case of this. It's actually corresponding to rank 2 here, and if just this funny contraction. So this is a generalization of something we've already seen. And next, I can also consider a closed loop. Namely, I start at a point, take an edge to the next point, and then actually come back to the same point. So how to obtain identities between these? Well, for genus 1, remember that we use translation invariance on the torus and momentum conservation. That was one set of identities. That's not available for higher genus. But instead, there is an exchange lemma or interchange lemma that allows you to move derivatives across a graph. And so it's this identity. So essentially, it's an identity that relates the x derivative of the Green's function to the y derivative up to stuff that factorizes as a function of x and y. And in fact, using this little lemma, which is really quite easy to prove, one can now construct an infinite series of identities for arbitrary genus and arbitrary rank. And I'm just going to give you the example of rank 2 here. So for rank 2, there is this identity. On the left side, we have one loop graphs. And on the right side, we have just linear chains. Okay, so now I have essentially 0 minutes left. So I'm just going to state in words, if we degenerate the genus 2 Riemann surface, there is separating and non-separating. Let me concentrate on non-separating. So I've written this out here. So this corresponds to degenerating the cycle B2 and letting it degenerate to a long cycle. Then the modular group reduces to a subgroup, which is in fact SL2Z semi-direct product with Z3, so-called Fourier Jacobi group. That's the group that leaves B2 invariant. It acts on the entries of the period matrix like so. This complex degeneration parameter is not invariant under SL2Z. And in fact, if you take a Siegel modular form and degenerate it, then the coefficients are not invariant, but exactly have the right transformation properties to correspond to Jacobi forms. We're interested in quantities that are more real. And in fact, there exists a real valued SL2Z cross Z3 invariant parameter T, given like so. And the separating node is characterized by letting T go to infinity. I give this parameter here for genus 2, but actually exists for any genus. So to make a long story short, in terms of this parameter, the degeneration of these genus 2 modular graph forms is in terms of a Laurent series in this parameter T of finite degree. Its degree is W and minus W. This is a non-trivial result that the degree is finite. Its coefficients are objects that transform under SP4Z, but under the group that leaves T invariant, they are in fact invariant. So these objects are our good old friends, the elliptic modular graph functions. Okay, so since I'm out of time, I'm going to summarize here. So I hope I have convinced you that the low energy expansion of string theory reveals a rich structure at genus 1 of modular graph functions and forms, at higher genus of modular graph functions and tensors. Now, there are lots of things that immediately flow out of this, but I have not been able to discuss because of lack of time. Physically, of course, we want to integrate. For example, for genus 1, we want to integrate over the genus 1 moduli space. This is, of course, not new. This goes back to Rankin-Zellberg, to Zagier, and so on and so forth. Having done these integrals in recent papers, one can draw conclusions about the behavior as a function of transcendental weight of these amplitudes. One can integrate over genus 2. Boris discussed that to some extent, and I just said it in words. And there are many, many papers reviewed to a large extent by in the talks of Stephen and Boris about matching the predictions of perturbation theory with the predictions of S-duality and supersymmetry, for example, in type 2b. This is an ongoing saga. And finally, something that I did not at all discuss, there are relations with super Yang-Mills and supergravity amplitudes, for example, gotten by taking the tropical limit that Boris discussed. And again, there are many, many papers. Perhaps the most interesting, outstanding question for this conference, at least, is what is the arithmetic significance of any of these? And to that, I don't have an answer. And on that, I want to thank you.
Thank you very much. So let's take virtual applause, and now I can call for questions or maybe answers. anyone who has a question, please feel free to speak up.
I may have one. Eric, you mentioned a congruent subgroup in the beginning. So in string theory, we would like to see that as from orbifold theory. So do you have an idea of the generalization of this kind of material for orbifold theories?
You mean for compactification of let's say 4 or 6 dimensions of our 10 on an orbifold? Is that what you mean?
Yeah, exactly. Yeah, I mean orbifold.
Right. So so of course to genus 1, a lot is known since you know, the mid 80s. On genus 2, Fong and I did, and also Edward Witten a number of years ago investigated the cosmological constant in the heterotic string for, you know, genus 2 on Calabi-Yau type orbifolds in 6 dimensions. And that actually gives rise to all kinds of new modular forms as well. But so I think not that much has been done beyond that I'm aware of. It would be interesting.
Thank you.
May I have a very naive question? You gave the physical explanation of poles in the Sij plane as exchange of massive string states. Could you elaborate on what exchange of massive string states means a little bit, please?
Well, I probably should have had an iPad here to draw this, but the simplest exchange is when you have 2 particles or strings meet in a vertex, and then you have an intermediate particle propagating, and then that particle again splits. It's this kind of well, double V. I'm really sorry I didn't draw this. And so that exchange as a Feynman diagram produces a pole, because there is just a single propagator in the middle. And when the momentum square approaches the mass of that particle, then that produces a pole. And so in string theory, there is basically for every, in the normalization I used, for every integer, positive integer value, there is a multiplet of massive particles, and each of them produces a pole. Does that answer your question to some extent?
Yes, and I will bother you again in the discussion session. But and so, if it's easy to explain, what do the branch cuts mean in the Sij plane?
Okay. Yes, good question. So basically, in physics, the branch cut is when you have the creation of 2 particles, but then they annihilate one another again. And so either they can annihilate or not. I mean, they don't have to, but so basically that means that there is, if the initial energy and momentum are fixed, then you know, you basically have a range of possibilities in the final states for the momenta. And so that's why you get a branch cut. So it corresponds to the creation of real particles.
Thank you.
Okay, so I'm sure there are many further questions, but we can put them into the discussion session later today. So let's thank Eric again for a beautiful talk.
Thank you.
We'll now take a short break, a 15-minute break until it's 4:45 Cambridge local time, when we will meet again for the next talk.
We're very happy to have Edward Witten talking now. Thank you, Ed.
Okay, thank you. So first of all, thanks very much for the invitation to this conference. and I'm glad to have the chance to speak. So I'm going to be explaining work with David Agayata, which hopefully will appear soon, where we're trying to understand a quantum field theory perspective on a picture that's been developed by Eddinghoff, Frankel, and Kazdan about an analytic version of the geometric Langlands correspondence. There are various earlier developments, but the only one I'm citing here is the one that's most related to physics by Teschner. I have not attempted to provide math references. So in the gauge, I'm going to begin by reviewing the gauge theory approach to the traditional version of geometric Langlands. That'll be roughly the first half of the talk. And then in the second half of the talk, I'll explain how to adapt the construction to interpret in the same language the work of Eddinghoff et al. So in the gauge theory approach, the starting point for usual geometric Langlands is n equals 4 superammules theory in 4 dimensions with the gauge group G, or with the GNO dual group G dual. By the way, we're in the midst of the outbreak of the 17-year cicadas, and I'm closing a window because I suspect you're hearing a lot of cicadas from outside. I wonder if that reduced the background noise noticeably. So
I think. Yeah.
Okay, the theory based on G has a gauge coupling constant E, a real parameter, and a topological angle theta, and they combine to a parameter tau, a complex parameter in the upper half plane. So there's an elementary symmetry of shifting tau by 1, which has to do with the fact that the insulin number is integer valued. And similarly, the dual theory has an analogous parameter, T dual, also with an elementary symmetry. The claim of electric-magnetic duality, which goes back to Montonen and Olive, is that the theories based on G and G dual are equivalent under tau going to -1 over tau, well, times this integer ng, which is it's 1 for simply laced G, and otherwise it can be 2 or 3. Now, this isn't particularly a statement about geometric Langlands, and people studying this duality are usually studying questions that have no obvious relation to geometric Langlands. But we can specialize to the situation that leads to geometric Langlands. To do that, first we consider a topological twist that leads to a CP1 family of topological field theories, parametrized by complex parameters psi or psi dual. If we study the whole family, then first we get this highly quantum equivalence under psi dual equals -1 over psi times the same integer n sub g. We also have these elementary symmetries. And this becomes the duality of what's called quantum geometric Langlands. But for today, we'll consider the basic duality between psi equals 0, which I'll call the A model for G, and psi dual equals infinity, which I'll call the B model for G dual. So what ingredients will we meet in this duality? In general, in quantum field theory, in dimension D, we associate a number to a D manifold, a vector space of physical states to a D-1 manifold, and a category of boundary conditions to a D-2 manifold. In the present context, though, although we'll be on a 4 manifold, we're only going to consider 4 manifolds of the form sigma times C, where C is a fixed oriented 2 manifold. Sigma will be some other 2 manifold. So effectively, we'll be doing topological field theory on sigma with C as a parameter. So that means that we'll have a category of boundary conditions on sigma that depend on C. So it's convenient to draw 2-dimensional pictures where I only draw sigma and not C. So here are a few pictures. A basic one is that sigma might have a boundary. In that case, to formulate quantum field theory on sigma, we need to specify a boundary condition. So that will be an object in the category of boundary conditions. Well, the reason boundary conditions make a category from this point of view is that if we're given 2 boundary conditions, then we can consider a strip. So we have a 1 manifold whose ends are on the 2 boundaries labeled by B1 and B2. It goes on in the future in the time direction. But remember, there's a vector space in codimension 1. In 2 dimensions, codimension 1 means a 1 manifold, in this case, an interval ending on the 2 boundaries. And if you like categories, you say that that vector space is Hom from B1 to B2. So again, there's a Riemann surface that's hidden in this picture. So everything in sight depends on a Riemann surface. So in particular, so does this Hom space. Now with this definition, Hom from B to B is an algebra for every B. So in this picture, we take two open strings ending on B on both ends, one here and one here, and they join together via this simple Riemann surface to make a single one. That's in category theory would be called multiplying two elements of Hom from B to B to make an element of Hom to B to B. So the picture is meant to explain why Hom from B to itself is an algebra. And moreover, although I haven't drawn the pictures, which would be the same picture with different labels, Hom from B to B prime is a left module for Hom from B prime to B prime, and so on. So electromagnetic duality will give an isomorphism between a category curly C associated to the Riemann surface C in the G theory at psi equals 0, and a dual category C dual associated to C in the dual theory at psi equals infinity. In addition, there's a natural mapping between certain natural functors on C and C dual. These functors come from what physicists call line operators. In a quantum field theory defined on a manifold M, a line operator is some sort of modification of the definition of the theory along an embedded one manifold K in M. The natural line operators at psi equals infinity are Wilson operators. A Wilson operator is the holonomy of a connection interpreted as an operator in quantum field theory. The natural line operators at psi equals 0 are the dual 't Hooft operators. So in physics, Wilson and 't Hooft operators are usually used to analyze questions like the confinement of quarks in atomic nuclei and other subtleties involving universality classes of quantum field theories. But for us, a line operator is a functor from the category of boundary conditions to itself. So I've drawn a picture which is intended to explain that. So in A, I'm trying to explain why a line operator gives a mapping from an object in the category of boundary conditions to a new object. So B is a boundary condition. Then I consider the special case where T runs along the boundary. We don't have to, it could be any embedded one manifold, but to get this statement, we take T to be living at a point in the Riemann surface C, but in sigma, it's a one manifold that runs along the boundary. And in topological field theory, there's no meaning for the distance between B and T. You could move T all the way up to the boundary, and then it defines a new boundary condition, T times B. That explains how T acts on objects of the category. The point of B is to explain how T acts on morphisms of the category. So although this is a slightly different picture from the one I explained before, you can think of a morphism as a point on the boundary that gives a junction from a boundary condition B to a boundary condition B prime. In the previous picture, the morphism is sort of another open string that joins on. But by conformal mapping, I could replace this with, I can conformally map that external open string to a point junction. So another picture of a morphism is that it gives a junction from one boundary condition to the next with some local data you have to supply at that point. And that local data is an element. Well, if you want to express these pictures in terms of categories, you say the local data defines an element of Hom from B to B prime. In any event, okay, and then here I've composed Hom from B to B prime with Hom from B prime to B double prime. But now the picture shows we could move T up to the boundary, and then we'd get a junction from TB to TB prime. So that's meant to explain that T acts on morphisms in the category. So I hope I've succeeded in explaining why a line operator behaves as a functor from the category of boundary conditions to itself. So I've been drawing pictures in 2 dimensions, but there are 2 more dimensions not drawn. And T really depends on the choice of a point, P, in the Riemann surface C. Such pictures make it obvious that the line operators T of P and T of P prime commute as functors on the category. You see, in a purely 2-dimensional picture, okay, well, I've drawn a purely 2-dimensional picture that describes acting on a boundary condition B with first T of P and then T of P prime. In purely 2-dimensional terms, there's an ordering of the two line operators, one if to the left of the other and closer to the boundary, and in general, functors would not commute. But here, T of P and T of P prime depend on the choice of points P and P prime in the Riemann surface C not drawn. And then if P is not equal to P prime, you can move the two past each other with no singularity because in 4 dimensions, they're not meeting. So you learn that T of P times T of P prime acting on a boundary condition B is the same as the two T's acting in the opposite order. That's obvious if P is not equal to P prime, and therefore it's also true by limit if P equals P prime. So the two dual categories, C and C dual, are equipped with dual families, T of P and W of P of functors, parameterized by the choice of P in C and some other data, and commuting at distinct points. So T of P corresponds to the usual Hecke functors of geometric Langlands, and W of P is its dual in the usual geometric Langlands duality. Now these functors depend on more data. W depends on the choice of a representation R of the dual group. So likewise, T depends on a choice of representation of the dual group. So you could consider two Hecke functors at the same point for possibly different representations. They still commute by a limit argument since they would have commuted at distinct but nearby points. Now the duality says that the algebra of composition of Hecke operators at the same point is the same as the corresponding algebra of composition of Wilson operators at the same point. And that, on elementary grounds, is the tensor algebra of representations of the dual group, where the tensor product of the two representations can be expanded as a sum of irreducibles. So the product of the two Wilson operators can be written as a sum of Wilson operators for irreducibles. The fact that the decomposition of the Hooft operators match that of the Wilson operators is known as the geometric Satake correspondence. So, Michael, do we usually take questions during the talk? I'm not hearing an answer, but anyway, if there are any questions, feel free to ask them during the talk. Now, to go into a little more detail, I want to introduce a useful language for formulating a simplified version of geometric Langlands duality. So let M sub H be the moduli space of Higgs bundles. So if the group is G, I'll call it M sub H of G and C, or just M sub H of G for short, where G is the gauge group, which for physicists is a compact form of the Lie group. So Hitchens showed that the Higgs bundle moduli space is a hyperkähler manifold. In one complex structure, it parameterizes Higgs bundles. In another complex structure, it parameterizes flat bundles over C, with the structure group being the complex Lie group G sub C. So the two complex structures, together with their product Ij equals K, act as the usual unit quaternions and are part of the hyperkähler structure. There also are the three corresponding Kähler forms, omega I, omega J, and omega K. So geometric Langlands duality for many purposes is a mirror symmetry between the A model of the Higgs bundle moduli space for G and the B model for G dual for particular symplectic and complex structures, which in Hitchens notation are omega K on the symplectic side and J on the complex side. This instance of mirror symmetry was first studied mathematically in this paper. So you can definitely ask questions for which the two-dimensional picture is inadequate. Mathematicians describe this by saying that the theory should be formulated on the stack of G bundles, bun G, not on a finite dimensional moduli space. Physicists describe it by saying that the correct formulation is as a duality of four-dimensional theories. 4 is the minimum. There's a 6-dimensional formulation that explains some things better, but 4 is sufficient for a complete statement of the duality. The two descriptions by a stack or a 4-dimensional gauge theory are not as different as you may think, because Atiyah and Bott showed in a well-known paper that a model of bun G is the space of all connections on a fixed smooth G bundle E over C. So four-dimensional gauge theory, which can be thought of as two-dimensional theory where the fields live on an additional two-dimensional space C, can be thought of as a two-dimensional theory with target bun G. So if you're a physicist, the talk about the stack of G bundles is just a mathematician's way to say that you really are doing four-dimensional gauge theory, not a two-dimensional sigma model. A two-dimensional sigma model is a useful approximation for many purposes, but the real statement is a four-dimensional gauge theory. Now, there's another bit of background we'll need before we try to get to Edinger, Frankel, and Kazhdan. I want to use the two-dimensional description of geometric Langland's duality as mirror symmetry between the Higgs bundle modular space and its dual for the dual group to motivate the statement that the category that appears on the automorphic side of the duality is a category of D modules. So on the automorphic side, we're discussing simply the A model or Fukaya category. Well, the approximation that's best developed mathematically is the Fukaya category of this modular space. And then the familiar A branes are the Lagrangian branes supported on a Lagrangian submanifold L. But Kapustin and Orlov discovered that to make mirror symmetry work, you have to introduce also coisotropic A branes that are supported on a coisotropic submanifold of Y that's above the middle dimension. The construction of coisotropic A branes is delicate in general, but the simplest case is the case that we need. The simplest case is that Y is actually a complex symplectic manifold with complex structure I and a holomorphic symplectic structure that I'll call omega J plus I omega K. My notation is as if Y is hyperkähler, although here I will be making a statement that doesn't really require that. Anyway, the simplest case is that we have this set up, and we're viewing Y as a real symplectic manifold with a symplectic form that's the imaginary part of a holomorphic 2 form. Then you take the B field of the sigma model to be the real part of the holomorphic 2 form. With this data, you can construct a canonical coisotropic A brane, which I'll call B sub CC, whose support is all of Y. It has the property that roughly Ham from BCC to itself is related to deformation quantization of the algebra of holomorphic functions on Y. More specifically, you can show that if Y is a cotangent bundle of some other complex manifold, then the sheafified version of Ham from BCC to itself is the sheaf of holomorphic differential operators on W, well, holomorphic operators acting on sections of K to the 1/2, where K is the canonical bundle of W. So for geometric Langlands, Y will be the Higgs bundle modular space. It's birational to a cotangent bundle, the cotangent bundle of the moduli space of holomorphic G bundles on C. So then A will be the sheaf of holomorphic differential operators on the finite dimensional moduli space. That means also that if B is any other A brane, then Ham from B to BCC will be a D module. That is a module for the sheaf of holomorphic differential operators. So that means that the category on the automorphic side of the geometric Langlands duality will be a category of, roughly speaking, D modules on the ordinary moduli space of bundles. Now, mathematically, you should work with D modules on the stack bun G, not on a finite dimensional space. Physically, what that means is that it's important that a version of this coisotropic brane can be defined directly in 4 dimensions, not only after reducing to a 2-dimensional description. Kapustin and I had a version of that in our original paper, but Gayotto and I improved it a few years later in this paper. And that enabled us to answer a question that had been unclear physically. The answer to this question had been known mathematically, but was unclear physically, and will be important later in this lecture. What's the dual of the canonical coisotropic brane itself? So as I said, the canonical coisotropic brane is an A brane, so its dual will be a B brane, that is a coherent sheaf or a complex of coherent sheaves on the Higgs bundle moduli space of the dual group. Well, Bailenson and Drinfeld had shown mathematically what's the dual. Well, the D module corresponding to BCC itself is the sheaf of differential operators. And its dual, well, the sentence starting from here is what Bailenson and Drinfeld had essentially showed. That if you take the differential operators regarded as a D module, then its dual is the structure sheaf of the variety of O pairs, which is a very special Lagrangian submanifold of the Higgs bundle moduli space. I'll call it L sub O, the Lagrangian variety of O pairs. So a gauge theory explanation of that was initially unclear, at least to me, but Gaiuto and I found one in this paper. So I wish there was time to explain all this more, but there isn't if I want to get to the more current developments. But I'll summarize this by saying the following. The main ideas in the gauge theory geometric Langlands correspondence are the following. The first is electric-magnetic duality between the group and the dual group of supersymmetric gauge theory in 4 dimensions. Twisting to make a dual pair of topological field theories. Compactifying to 2 dimensions on a Riemann surface C. The dual pairs have dual sets of line operators with 't Hooft operators on the G side and that correspond to geometric Hecke transformations, and dual Wilson operators on the other side that correspond to representations of the dual group. On one side of the duality, there's this distinguished brane BCC that establishes a map from A branes to D modules on bun G. On the other side, one is studying B branes in the complex structure in which you're considering flat bundles with complex structure group. So these are the main ideas of the correspondence as much as I can explain it today, but I should try to stop for questions just for a moment. I assume people can unmute themselves and ask questions if they want. Is that the case, Michael?
Yeah, they can indeed.
Okay, but I'm not hearing questions. So if that is the case, I'll just go on. Well, the story as I've explained it so far involves deformation quantization, not quantization. But in proceeding, it's really important to discuss quantization rather than deformation quantization. And I want to pause to explain the difference because even though it's elementary, I do find it can cause confusion. So I'm going to consider a concrete example of a two-sphere. So here x, y, and z are simply real variables. And I consider the two-sphere x squared plus y squared plus z squared equals j squared, viewed as a symplectic manifold with its usual rotation invariant symplectic form, which we can write as simply dx dy over z, although that way to write it doesn't exhibit the rotational symmetry. In deformation quantization, we start with the commutative algebra of functions, which here you can think of as polynomials in x, y, and z, complex valued polynomials, and we want to deform it to a non-commutative algebra. In general, you specify that the leading non-commutative deformation should agree with the Poisson bracket, and then we ask if there is a family of associative algebras over C of H bar or maybe C double bracket of H bar with that property. So this would mean that you can set H bar to an actual number, and this would mean that you have to work over formal power series in H bar, and that you get a formal family of algebras, but not an honest algebra with where you can set H bar to a number like 1. So in the present case, we can just write down the answer, which is given by the SU2 Lie algebra. So that's a family of associative algebras over a C of H bar. H bar, in other words, it makes sense with H bar interpreted as a complex number. To these relations, we should add the fact that x squared plus y squared plus z squared is j squared. Now, that's deformation quantization. It's not quantization where you would have a Hilbert space that the algebra acts on. And in this generality, quantization isn't possible because I haven't put any condition on j, which could be an arbitrary number. In fact, if we let x, y, and z be complex variables and with complex polynomials, j could be an arbitrary complex number. But in the setup I gave for the two-sphere with its usual symplectic structure, J was an arbitrary real number. In that generality, there's no quantization. Quantization means finding a Hilbert space H, which is supposed to have the appropriate size. Its dimension is roughly the symplectic volume of the phase space that the algebra acts on. That does not exist for arbitrary J. To construct H, one has to quantize the parameter J, set it to preferred values at which the Hilbert space exists. These special values correspond to the angular momenta in the real world of electrons, atoms, molecules, and so on. So physically, X, Y, and Z could be the generators of angular momentum, or the angular momentum charges, conserved quantities. This is the algebra of the angular momentum generators. But in the real world, angular momentum has preferred values. It's quantized. Quantum mechanics got its name because the parameters are quantized. In deformation quantization, J was not quantized, but in quantization, where you want a Hilbert space, J is quantized to special values at which this algebra has a nice Hilbert space representation.
Question?
Yes?
So if you allowed an infinite dimensional Hilbert space, then you would not have this quantization of J. So part of the classification is that the Hilbert space be of the appropriate size.
Yes, which I didn't want to explain. So you see, if we wanted to discuss in this framework, for example, unitary but infinite dimensional representations of SL2R, we would not begin with this real orbit. We should begin with an orbit of SL2R. And my statement about the appropriate size was too crude if we're interested in the infinite dimensional case. I was trying to avoid getting to a point like that. What did I do? I somehow went to the beginning. Well, since I'm stuck trying to scroll through to the right points, this is a good moment for another question if there's one. Anyway, that's the difference between quantization and deformation quantization. And just remember, quantization got its name because the parameters are quantized, which isn't the case in deformation quantization. So Gukov and I asked whether the A model in this general setup can describe quantization and not just deformation quantization. And the answer is yes, under certain conditions. Recall that in general, up to this point, we have a complex symplectic manifold, which in geometric Langlands would be the moduli space of Higgs bundles. But for the moment, it could be any complex symplectic manifold. And then to get deformation quantization, we viewed Y as a real symplectic manifold with the symplectic form, which is the imaginary part of the holomorphic symplectic form. And then the A model provides a framework for deformation quantization of Y. To get actual quantization, we need something more. So let's discuss Lagrangian A branes. That means branes supported on a Lagrangian submanifold of Y, a submanifold that's Lagrangian for M omega. So we're viewing Y as a real symplectic manifold with this real symplectic form. So L being Lagrangian in general just means it's Lagrangian for M omega. In many examples important in geometric Langlands, L is actually a complex Lagrangian submanifold. That is, it's Lagrangian for omega, not just M omega. For example, if you take a skyscraper sheaf on the dual side, supported on a point in the Higgs bundle moduli space, its dual will be a Lagrangian brane supported on a fiber of the Hitchin fibration. That's a complex Lagrangian submanifold. This happened because a point in a hyperkähler manifold is hyperholomorphic. It's holomorphic in every complex structure. So these branes are very important in geometric Langlands. They're the eigenbranes, the Hecke eigenbranes. Hecke eigenbranes correspond to Lagrangian branes that are Lagrangian in the complex sense. And that's because they're dual to a sheaf supported on a point in the moduli space of local systems. But a point is holomorphic in every complex structure. And that'll be dual to the fact that we actually get a complex Lagrangian brane. So some very important objects are complex Lagrangian submanifolds, but in general, for an A-brane, L need not be Lagrangian for omega only for its imaginary part. Just as generically, a coherent sheaf on the Higgs bundle moduli space isn't hyperholomorphic. In fact, in usual discussions of geometric Langlands, people don't even mention the notion of something being hyperholomorphic. So in geometric Langlands, the ones that are complex Lagrangian are very important. But Gukov and I considered the opposite case of an A-brane whose support M is Lagrangian for M omega, as it must be by definition of an A-brane, but symplectic rather than Lagrangian for real omega. So that's the opposite case from the case I just mentioned. We argue that in this case, Hom from B to BCC represents a quantization of M with the symplectic structure real omega. See, first of all, if M is symplectic for real omega, then it makes sense to try to quantize it with that symplectic structure. And we claim that such a quantization is in fact provided by the A model of the complexification of M. So for example, if Y is an affine variety which has a lot of holomorphic functions, they're deformation quantized to get Hom from BCC to itself. For any A-brane B, Hom from B to BCC will be a left A module. Well, see, if M is such a real Lagrangian submanifold of Y, that means you can view Y as a complexification of M. So holomorphic functions on Y are analytic continuations of certain real analytic functions on M. There are enough of them to get a reasonable quantum deformed algebra of observables, and that's the algebra that acts on this H. So I'm afraid I've highly compressed that, but that was how we interpreted quantization in terms of the A model. So, well, Hom from B to BCC is an A module that one can show has appropriate properties to be a quantization of M, except you need one more condition if you want it to be unitary, if you want H to be a Hilbert space, not just a vector space that's an A module. So I've omitted a key point, which is what structure we need so that this H is a Hilbert space and not just a vector space. In general, if B1 and B2 are any two branes, there is a non-degenerate bilinear, not Hermitian pairing between Hom from B1 to B2 and Hom from B2 to B1. To get a Hermitian product is the same as finding an antilinear map from one to the other. So we showed that there's such an antilinear map, which I'll call theta tau, if Y has an anti-holomorphic map with M as a component of its fixed point set. I won't explain the definition of theta tau, but I'll explain why one should expect the existence of such a tau to be the right criterion. If holomorphic functions act on Y, act on H, and H is a Hilbert space, then there will be a notion of which holomorphic functions on Y act as Hermitian operators. Existence of tau gives such a notion. A holomorphic function on Y is real if it's real when restricted to M. So that was what we needed to define Hermitian pairing. And given such a tau, the Hermitian product on Hom B1, B2 on any pair of tau invariant branes is defined using theta tau, the antilinear map that comes from tau, and also the bilinear pairing of the A model. So I've left out a lot of steps. I didn't explain the role of CPT. This pairing is always non-degenerate, but in this generality, it's not positive definite. And for the specific case relevant to quantization, we expect positivity because we're close to a semi-classical limit of quantizing a cotangent bundle. So in this approach to quantization, if you're given a real symplectic manifold that you want to quantize, you have to first find a complexification of M to a complex symplectic manifold Y with some appropriate properties. And then you can use the A model of Y to quantize M. So the main property you need for Y is simply that it does have a good A model. And that's a subtle condition. So we don't know general necessary and sufficient conditions for that. We can only give sufficient conditions at a physical level of rigor. We could compare this loosely to geometric quantization, which is the closest there's been to a systematic approach to quantization. In geometric quantization, to quantize M, you have to find a polarization of M, roughly a maximal set of Poisson commuting variables. Given a polarization, geometric quantization gives a recipe of quantization. So either geometric quantization or quantization by branes can give good results if there's a natural polarization in the case of geometric quantization, or natural choice of the complexification in the case of quantization by branes for the problem at hand. Now, I'll say one more thing before I try to tell about the work of Eddinghoff, Frankel, and Kazhdan. A limitation in my paper with Grukov is that we didn't understand very much about comparing brane quantization to geometric quantization. Now, as I said, Gallardo and I were motivated to look at this more closely as background to understanding the work of Eddinghoff et al. At some level of precision, we were able to compare quantization by branes to geometric quantization in the following sense. If M can be quantized both ways, in geometric quantization using a polarization P, in brane quantization using a complexification Y, then you'd like a criterion that would show that the two quantizations agree. And I'll simplify the statement slightly, but basically we showed that if P can be analytically continued to what we call a homomorphic polarization of Y, then the two quantizations agree. Geometric quantization of M using the polarization P is equivalent to brane quantization of M using Y. Now, all this is by way of preparation to talk about the work of Eddinghoff, Frankel, and Kazhdan that I mentioned at the start. But maybe I'll give you another chance for questions before I go into that. Well, if there are no takers, I hope that's not because everyone...
Sorry, I have a question. So what exactly does it mean for the quantizations to be the same? I mean, all Hilbert spaces are isomorphic. Is there some natural operator algebra?
Yes, of course. There are operators that act on each side. For brane quantization, I told you what acts. And geometric quantization also gives an answer for what acts. And in this situation, they agree. So, Eddinghoff, Frankel, and Kazhdan considered a Hilbert space H of L2 functions, or better half densities, on the moduli space of stable homomorphic G bundles over C. It's more natural to call them half densities, but because this moduli space has a natural measure, because it has a natural Kähler structure, you could simply call them functions. Then they constructed operators on H that are related to the usual constructions of geometric Langlands, and found interesting dualities, theorems, and conjectures concerning the action of these operators. So I really wouldn't have time to tell you what all their statements were. Rather, I'm going to proceed with the physical picture. As we proceed with the physical picture, we'll see what those statements might be. So I'll explain what they did in the context of explaining a physical interpretation of it. So in geometric quantization, you'd understand L2 functions or better half densities on M of G in terms of quantization of the cotangent bundle T star of M of G, which is in an L2 theory can be thought of as the Higgs bundle moduli space, MH of G. So in other words, the Hilbert space of EFK is what you get if you take the Higgs bundle moduli space MH of G with the real symplectic structure M omega and quantize it by geometric quantization using the fact that it's a cotangent bundle. So then EF and K studied natural operators on this Hilbert space and made duality statements about them.
Sorry, I have a question. So that's only, I thought those were only birationally equivalent. That doesn't matter for this?
Well, in an L2 theory, that's not going to matter because in L2 theory, you can always throw away a set of measure 0. And birational equivalence means that they're the same except for a set of measure 0. On the other hand, if we're going to get anywhere in terms of predictions from duality, we need to understand the quantization of the Higgs bundle moduli space via branes. Now, remember, I told you that the first step to quantize anything by branes is to pick a complexification of it. In this case, the Higgs bundle moduli space is already a complex manifold. So we have a complex manifold which we're viewing as a real symplectic manifold, and we want to complexify it again. Well, any complex manifold viewed as a real manifold has a canonical complexification, namely y hat, which is y1 times y2, where y1 and y2 are two copies of y with opposite complex structures I and minus I. And y hat comes with an involution. I wrote u hat here, but it was meant to be y hat. Y hat comes with an involution tau that exchanges the two factors. And since the two factors have opposite complex structures, this is an anti-holomorphic involution, and it leaves fixed the diagonal. So we have the starting point of brane quantization we get for free. Namely, we simply replace y by the product of two copies with opposite complex structure and view that as a complex manifold that has an anti-holomorphic involution that leaves fixed the original y. So as I said, the fixed point set is the diagonal in y1 times y2. Since the complex structures on the two factors are opposite, we can take the holomorphic symplectic form of y hat to be what I'll call omega hat, which is 1/2 omega on one factor and 1/2 omega bar on the other factor. So omega is the holomorphic 2 form of y. I take 1/2 omega on one factor, 1/2 omega bar on the other factor. So that's holomorphic in the complex structure of y hat. Then the restriction of omega hat to the diagonal is real omega. In other words, the diagonal is a copy of y that's Lagrangian for m omega and symplectic for real omega. So this is the appropriate situation where the A model of y hat is appropriate for brane quantization of y viewed as a real symplectic manifold with a symplectic structure real omega. So that's the situation in which quantization of y using a Lagrangian brane B supported on y makes sense. Moreover, I told you that there was a certain condition under which geometric quantization agreed with brane quantization, and that condition is satisfied here. So that sentence is meant to explain why EF and K studied the geometric quantization of y using a natural real polarization, which was part of Hitchin's description. But what I'm explaining is why geometric quantization using that real polarization is equivalent to brane quantization in this setup here. So the Hilbert space they study is the one that would arise in brane quantization. However, we have to ask what are the observables in brane quantization. Let's recall Hitchin's integrable system. The Higgs bundle moduli space has a Hitchin fibration pi from Higgs bundle moduli space to a certain base, which is Cn for some n. The linear functions on B are Hitchin's commuting Hamiltonians. Classically, the global holomorphic functions on the Higgs bundle moduli space are just the pullbacks of functions on B. So the algebra A0 of holomorphic functions on the Higgs bundle moduli space are just the polynomial functions of the classical Hitchin Hamiltonians. What are the quantum observables in brane quantization? Well, for brane quantization, we define the canonical quasitropic brane of y hat, which is y1 times y2. It's just a product of canonical quasitropic branes for the two factors. So the algebra that will act on quantization is just a product A tensor A bar, where A is A is the same thing for canonical quasitropic brane of y1 and A bar for y2. The quantum deformed versions of A0 and A0 bar, the holomorphic and anti-holomorphic functions on y. However, for the Higgs bundle moduli space, you can show that the quantum deformed rings are still commutative. That's due to Hitchin for SL2 and to Bailenson and Drinfeld for in general. And Kaposta and I also gave a gauge theory explanation. So the quantum deformed objects are the commuting differential operators, which are the quantization of Hitchin's classical commuting Hamiltonians. So we want to understand the action of A tensor A bar on the Hilbert space, which, because of the equivalence to geometric quantization, is the same as the half densities on the ordinary moduli space. First of all, there's no mystery about the fact that A tensor A bar does act on the Hilbert space. That's just the statement that holomorphic and anti-holomorphic differential operators can act on functions on the moduli space. Well, better here half densities, but it comes out to be the same. Holomorphic operators trivially commute with anti-holomorphic ones, and the algebras of holomorphic and anti-holomorphic differential operators are separately commutative. So there's no mystery about the fact that A tensor A bar acts on the Higgs bundle moduli space as a family of commuting operators. But what are the joint eigenvalues of Hitchin's Hamiltonians and their complex conjugates? To answer this question, we want to apply duality. To apply duality to Ham from B to BCC, where BCC is the product of the two quasitropic branes and the two factors, and B is the Lagrangian brane of the diagonal, we need to understand the duals of the three branes involved. So these two are the branes associated to the ring of holomorphic functions and anti-holomorphic functions for the other one. And as I explained before, the dual is the structure sheaf of the variety of O pairs. An O pair is a flat bundle whose holomorphic structure obeys a certain condition that I will recall in a few minutes. And BCC2 is similarly related to deformation quantization of the ring of anti-holomorphic functions. So its dual is the structure sheaf of what I call L O pair bar, the Lagrangian submanifold that parametrizes flat bundles whose anti-holomorphic structure obeys the O pair condition. What about the brane B supported on the diagonal? There's an unfolding trick that shows we don't have to worry about it. So we had two copies of the A model of Y that were totally decoupled, except that the brane B was supported on the diagonal. So think of each of the two copies as living on a strip, but the two strips on one boundary are glued together by the fact that the boundary condition says that the two boundary values are equal for the two theories. If I unfold it, I just have a single theory on a strip of twice the width, with BCC1 on the left, BCC2 on the right. I've drawn the diagonal line here in the middle of the strip, but nothing's happening there. Because the boundary condition just said that the boundary values on the two sides were equal there, and you can just forget about it in this picture. The boundary condition just says that the fields are continuous in the middle, which is what you'd have assumed if you just erased that line. In the unfolded picture, there's just a single copy of the Higgs bundle moduli space, and the Hilbert space is Ham from one quasitropic brane to the other, where BCC is the quasitropic brane for one complex structure, and BCC tilde is adapted to the opposite complex structure on the same space. But they're both A branes in the same A model of the same space. So now we can easily dualize this. The dual of BCC is a Lagrangian brane, and the dual of BCC tilde is another Lagrangian brane, namely the variety of O pairs and the variety of anti-holomorphic O pairs. So A becomes Ham from L O pair to itself. That's just the algebra of holomorphic functions on L O pair, according to a celebrated result of Bailenson and Drinfeld. And A bar, likewise, is the holomorphic functions on L O pair bar. So here are the two dual pictures. In one picture, you have a strip with the two quasitropic branes on the left and right, and this is in an A model. The other picture is a B model picture, and there's simply two Lagrangian branes on the two sides. So, okay. Two branes that are supported on complex Lagrangian submanifolds on the two sides. And the Hilbert space is Hom from B tilde C. The Hilbert space, in one case, is Hom from here to here, but in the other case, it's just the intersections in the B model of two Lagrangian branes. And the intersections in the B model are simply supported on the physical intersections between the two Lagrangians. So LO pair and LO pair bar are Lagrangian branes. So Hom from one to the other is an intersection space. Actually, what it's written here is wrong. It's just a B model intersection space, which is more simple than a statement in Fourier cohomology. So here I've written a slide that elaborates upon the fact that the variety of O pairs and also the variety of complex conjugate O pairs are complex Lagrangian submanifolds in the same complex structure. That's because we're looking at the Higgs bundle moduli space and the complex structure in which it parametrizes flat bundles over with the structure grouping the complex Lie group. The flat bundle has both a homomorphic structure and an anti-homomorphic structure. And a condition on the homomorphic structure or on the anti-homomorphic structure, either one is a homomorphic condition from the point of view of the moduli space of flat bundles. Now, as I explained before, using the existence of the homomorphic involution tau, Hom from B tilde CC to BCC carries a Hermitian inner product, which we expect to be positive. The dual space likewise carries a non-degenerate inner product, which is defined in a similar way using the anti-homomorphic involution of the dual moduli space. But the positivity on the dual side is very subtle. For generic B branes, the non-degenerate inner product that you define is not positive definite. The conditions that make the Hermitian form positive were defined by Eddinghoff et al., who showed these conditions are satisfied for GL1 and for SL2. So if you let X be a point in LO pair intersect LO pair bar, it corresponds to a flat bundle E. That's an O pair both holomorphically and anti-holomorphically. The anti-holomorphic involution that's used to define the Hermitian structure will map E to the complex conjugate flat bundle E bar, which is also an O pair both holomorphically and anti-holomorphically. If E isn't isomorphic to E bar, then they're both null vectors for the Hermitian form, which in that case is not positive definite. But the duality predicts that it should be positive definite, so we expect that as conjectured by EFK and proved in some cases, E is always real, that it's always isomorphic to E bar. So the claim is that flat bundles with complex structure group, this should be for the dual group, that are O pairs both holomorphically and anti-holomorphically, are actually real. That is, their structure group reduces to a real form. You can also show that positivity requires that the intersection points should be transverse. And that's also among the results and conjectures of EF and K. So a flat bundle that's an O pair holomorphically and anti-holomorphically and is also real is what they call real O pairs. So the claim is that the real O pairs correspond to the intersection points. And therefore, the joint spectrum of A and A bar corresponds to real O pairs. Recall that according to Bailenson and Drinfeld, an element X of the algebra of homomorphic functions has two interpretations. It's a holomorphic differential operator on Bunge, the moduli space of bundles, and it corresponds to a holomorphic function, f sub x, on the variety of O pairs. Similarly, an element of the corresponding anti-holomorphic algebra is an anti-holomorphic differential operator on the same space, and it corresponds to a holomorphic function, fx prime, on the variety of anti-holomorphic O pairs. So an intersection point P of the two Lagrangian branes determines a pair of eigenvalues for the differential operators x and x prime, namely fx of p and fx prime of p. And that's the proposal for the joint spectrum of Hitchens quantized Hamiltonians. Now, in all versions of Langlands correspondence, it's also very important to consider the Hecke operators. So EF and K introduce Hecke operators as operators on the Hilbert space H that arises in quantization of the Higgs bundle moduli space as a real symplectic manifold. I already explained that line operators of the four-dimensional gauge theory can be used to define functors on the category of branes. And that Houghton-Wilson line operators are dual pairs of functors. The same line operators represent operators on the quantum Hilbert space. I've tried to explain this with a picture. So before we had a line operator running along the boundary, it was a functor on the category of branes. The same line operator running from left to right defines an operator on quantum states. A quantum state goes in at the bottom after interacting with the line operator, comes out as a new quantum state at the top. So T is acted simply as a Hilbert space operator, an operator on quantum states. The next picture was aimed to explain what happens at the endpoints. There's some important structure at the endpoints in B, but I won't have time to explain that today. Now, the argument that showed that the functors corresponding to line operators commute for different points goes over immediately to show that line operators viewed as ordinary operators on quantum states also commute. It's simply the same, basically the same argument as before. Because they live at different points in C, they can be moved up and down in this picture without singularity. And moreover, as in the previous case, we can consider the case that P equals P prime as a limiting case. And a similar argument shows that Hecke operators, viewed as operators on quantum states, commute with the quantized version of Hitchens holomorphic or anti-holomorphic Hamiltonians. In a two-dimensional picture, it looks like there could be a problem in sliding an element of A represented as a local operator on the boundary past a Hecke operator TR of P. But in 4 dimensions, it's obvious there's no problem because X can be assumed to have support disjoint from T. Finally, we should ask what are the predictions of the duality for the eigenvalues of the Hecke operators. To answer this, we start on the dual side. We're going to find the eigenvalues of a Wilson operator acting on Ham between the two Lagrangian branes, and then the duality will predict the eigenvalues of the Hecke operators. Also, we'll find what kind of data is needed for the corners that make the Wilson operator to be an operator. Again, the duality predicts that the same data is needed to define the Hecke operator. So I now have to tell you what is a Wilson operator. If we have a G bundle E and we're given a representation of G, then we can form an associated bundle E sub R. And if G had a connection, then E sub R also comes with a connection. The corresponding Wilson operator for a path in our 4 manifold is defined by parallel transport of the connection along the path gamma. For the present application, we fix a point P and C, and we fix 2 points A and B on the left and right boundaries, and a path in sigma times P from A times B to B times P. So everything happens at a fixed point P inside C, but in sigma, we have a strip and a path from A times P to B times P. We take the holonomy operator from left to right. Well, in general, the holonomy operator along a path with endpoints is not a number. The holonomy is a linear transformation from the fiber at one endpoint to the fiber at the other endpoint. Now, I want to state this more symmetrically, so you can consider the holonomy to be a homomorphism from one fiber times the dual of the other fiber into C. The dual of the other fiber is the fiber for the dual representation. Now, a quantum operator will come from a complex valued function of connections, which this isn't. This is a linear function on a vector space, not a function. We don't have that yet. So far, we have a linear operator from a natural vector space to C. To get an operator, we have to supply elements in the two vector spaces. And then this linear transformation applied to the tensor product of the two vectors will be a function, a complex number depending on the data. Its quantization will be an operator. To avoid unnecessary details, I'll take the dual group to be SL2, and I'll take the two representations to be the two-dimensional representation. But there is a straightforward generalization to any group and representation. So in this picture, the boundary condition on the right boundary is that the G-dual bundle E is an anti-holomorphic O-pair on the right boundary. And that means by definition, and here I will finally give you the definition of an O-pair, that there is an anti-holomorphic non-split exact sequence, where K bar is the canonical bundle of C with opposite complex structure. K bar to the 1/2 is a square root. So we pick a vector in K bar to the 1/2, and that gives a vector J bar of V in the fiber at the left. Similarly, on the right, the bundle is a holomorphic O-pair, so there's a non-split exact sequence. So we pick a vector W in K to the 1/2, and that gives us J of W in the appropriate fiber. So once they're picked, we can apply the W that we had before, which was a linear transformation, to the vector J bar of V tensored with J of W. And that's the complex valued function of connections that we want to interpret as a quantum operator. That step is trivial because in the B model, because an O-pair is irreducible as a flat bundle, we can actually assume that the connection is pulled back from C up to a possible twist by an element of the center. So that means parallel transport from left to right does nothing, except possibly multiplied by an element of the center, which for the case that G dual is SL2 is plus or minus 1. So up to sign, W hat is just the dual pairing between the two fibers, which are simply two different ways of looking at the same flat bundle. And so the eigenvalue of W hat for this particular intersection point is just plus or minus the pairing in the two-dimensional representation between the two vectors we had. And therefore, the duality predicts that the eigenvector of the 't Hooft operator, well, first of all, that defining it requires the same data. And secondly, that the eigenvalues of the resulting 't Hooft operator are the same as we found on the dual side. So I probably zoomed through that a little bit too fast, but I hope to have given you at least a sense that the dual of the question of finding the eigenvalue of an 't Hooft operator is a problem that has a classical answer on the B model side. And having found that answer, that's going to be the prediction for the eigenvalue of the 't Hooft operator on the A model side. Thank you.
Thank you very much, Edward. Maybe we should begin with see if there are any questions for you, and then open the discussion more generally to the whole, to the other speakers. Greg.
Yeah, I had a question about the commuting differential operators A on L2 of M of G.
Yes.
So is that the center, the same as the center of the universal enveloping algebra and affine Lie algebra at the critical level? So does it have WZW interpretation?
Well, first of all, what you've just said is how Beilinson and Drinfeld proved the commutativity for general groups. Hitchin kind of did it for SL2 by a special case of that. Secondly, there is a natural way of looking at the physics that naturally leads to that construction, to that interpretation. It was developed in some of Davide Goeto's work in the last 4 or 5 years. so yes, there is, not only is there that interpretation, but that was the original interpretation by Balanson and Drenfeld.
So can you explain the connection to WZW3?
Well, it's not, the critical level is pretty weird in terms of WZW3. So it's not anything close to a physical WZW3.
Right, but I mean, it's always been a mystery to me. So I was wondering if this point of view.
I'm reluctant to get it. Nothing I've said in this lecture sheds any light. Your question has been elucidated in previous papers by Davide. I'm a little bit worried about giving a detailed answer as it gets too far from my actual lecture. But the basic idea is that corners support chiral algebras in this story. There's something important that I didn't explain in the lecture, which is that the twist in 4 dimensions gives a 4-dimensional topological theory. But we used in the lecture branes that were only topological in a 2-dimensional sense. They depended on the actual choice of the Riemann surface C. And so if you like, they were holomorphic topological branes. And if you take a corner between 2 holomorphic topological branes, they tend to support chiral algebras that live on the corner. That's the theme in a whole series of papers Davide wrote, some with different co-authors. And your question gets at that series of papers, really, rather than what I've done or what I've talked about today. I'm kind of reluctant to say more. It's a little bit hard to say more in a useful way.
Okay, yeah, I know what papers you're talking about. Thank you.
Any other questions? So Daniel, I think Daniel is going to lead the discussion now for the time being. Daniel, are you there?
I'm here. I'm here. Thank you. Okay, thanks a lot for this very nice talk.
I guess I'll unchair if we're going to a general discussion.
Yes, thanks. So we had this breakout room session yesterday that was very successful, and we're going to do that today again. But it was suggested that we actually take maybe 15 minutes to allow for everyone here in the main room to ask some questions to all of the speakers, because there wasn't really much time for questions during the talks. So we will just see how that goes, and I will allow anyone to unmute themselves and ask questions to the speakers. I think both Boris and Eric are present, and at least Jens Funke and Steve Miller are present from yesterday. So yeah, please, if there are questions, go ahead.